Okay, good morning, everybody. I think we should get started. Still some people dropping in. Okay, this is our second keynote talk. I'm very glad and we are very happy to have Jan-Michael Rost here with us to give this talk. He's one of the directors of the MPE for, well, Max Planck Institute for the Physics of Complex Systems. He's head of the Finite Systems group there, a very large research group dealing with well, finite systems, light-matter interaction on the atomic scale, maybe. And he was doing his PhD and habilitation in Freiburg with John Briggs, and that is where I got to know him a few years later. And today he will talk about the emergence of time and temperature from separation of system and environment. Is physics timeless? So please, Jan-Michael, go ahead.
Yeah, thanks a lot, Thomas, of course, for inviting me and giving me even so much time to talk about this, the keynote talk. And also thanks to all the organizers and to your students to put this meeting together. I know how much work this is, and I guess we have enjoyed this tremendously so far, including the dinner last night. And I said already, you have probably some connections to the sacred ecology because it only triggered last night, the rain. It was not really pouring, so very good. All right. So yeah, this is a talk you probably will not forget for the better or the worse, because it kind of claims that time is not fundamental. And I will try to convince you about this, and you're very welcome to argue against it. This is this inverse fragility or so, which would then come. Anyway, so this is work by Sebastian Gemsheim. He was a very gifted PhD student I was lucky to have. And he wanted to prove this kind of idea that time is relational, as you will see, quantum mechanically. So far, this was done semi-classically. This is also what I did with my former PhD advisor a long time ago. And others tried to do this as well. And this is now the full quantum version. And it extends also to temperature, meaning imaginary time. So what is this idea of relational time? If you think very abstractly, if everything is together, then this everything together cannot change. If something is still changing, you have not included it into everything. And that's the idea that a starting point is probably reasonable to say you have a state which is basically an eigenstate of some abstract Hamiltonian, and that describes everything. And then the question is, but how does then time come about? Because we all experience time and changing or change. And the idea is that this comes from splitting this everything, which is here this orange blob, into a system and its environment. And you see here, I do this in a certain way. So the orange apple is kind of the system. And I've cut out basically the system here by the environment. And this is because I will argue that the environment actually conditions the system. And this is important if you want to construct a wave function later on. And the idea is then that even complex time is a useful concept to capture the relation between system and environment. Now, what's the motivation for that? One comes really in literature from quantum field theory, and don't ask me about this because I don't understand enough about it. And there the idea is very similarly in a very large scale that the universe is kind of time independent and fulfills the so-called Wheeler-de Wit equation, which is formally an eigenequation for an eigenstate for the global state psi here. And this is a Hamiltonian constraint, as it's called. And translated to ordinary quantum mechanics, this means that we should be able to construct time evolution for the system from a global eigenstate of everything. And the same should hold true for temperature somehow. And the second motivation is maybe a bit more down to earth for people who do ordinary quantum mechanics. And this is how all this work started in a coffee discussion about the energy time uncertainty relation, which you probably all know is fake. It's just a Fourier relation because time is not an operator. While normally momentum and position, they are true operators in quantum mechanics. And the question is then, why is that the case? Why is time not also an operator? And why is this not equivalent? And then you can think about this. Of course, you have these conjugate pairs of observables. And in classical mechanics, you will not have this distinction, right? So that kind of suggests that classical mechanics is not sensitive to this origin of time. And so the question is, why is it first of all so for quantum mechanics? And what is different in classical mechanics? So in classical mechanics, we have our two heroes, of course, Newton. We get taught this very early on. We get kind of spoiled by this, or how to say, put in a certain direction, how to perceive time. And a bit later came then Poincaré. And I would argue if Poincaré would have been there before Newton, we would probably have a very different idea what time is. Because as you all know, Poincaré did dynamics in phase space. And you don't necessarily need time for that because formally you can always construct in classical mechanics a Hamiltonian, h equals 0, and by extending your phase space variables by the pair energy and time. And then if you have your original Hamiltonian, little h, time dependent, you subtract E, this will give 0. And that's this kind of extended phase space description, which is then of course, time dependent, but E and T are just equivalent to any kind of phase space pair, P sub I, Q sub I, whatever you want. And here you can see this if you have enough patience how to do this. So you can multiply essentially your new Hamiltonian, which is the value 0, by any function of phase space variables. And if you then calculate Hamilton's equations, you see that here Q dot, the velocity, gets multiplied by this function you have chosen. And if I, for instance, choose this function as 1 over p dot, then I get that the h by dp is dq by dp, or q, whatever, a new dot, where now the independent variable is the momentum. So I've switched from time to momentum as an independent variable, and I can use basically any variable in the system to describe my path instead of time. And time will then be a function of this independent variable. So this is possible, of course, classically. And therefore, you cannot decide classically if time is fundamental or emergent, since it's simply equivalent to all other variables. Now let's see what's happened in quantum mechanics. In quantum mechanics, you would say, no, it's not fundamental. Why? Because for that reason that Q and P are quantized, and with them the energy, our Hamiltonian, is quantized, but time is not. Time enters the time-dependent Schrödinger equation as a parameter, not as an operator. And this was, of course, discovered early on by our heroes in quantum mechanics. So Wolfgang Pauli commented on that in, what was it, in 1931, as you can see, a couple of years after the discovery of quantum mechanics. And he said in the older literature, it's very funny, you know, quantum mechanics was kind of 6 years old. He said in the older literature, sometimes it's stated that the commutator of Hamiltonian and time exists, but then he said this is actually, there's no operator which can fulfill this equation because you need eigenvalues from -infinity to +infinity continuously, and the Hamiltonian has often discrete eigenvalues, and therefore that's not possible. A more modern version is written down here, which is formulated in 2015, where it says essentially because your energy spectrum is bounded from below, that's a more elegant abstract version, you cannot have this. And as a little note on the side, of course, you might know the basically time delay operator, which is a derivative of the S matrix multiplied with its conjugate. That is kind of the delay time. And what this is exactly a relational kind of expression between two time independent systems, the free particle is measured relative to the particle in the potential. So that's a time expression which is valid also as an operator, but it's already a relation between two different systems. So now we want to prove that time is emergent as relational between a system separated from its environment. And how do we do this? Essentially by deriving the time-dependent Schrödinger equation for the system from the time-independent one, what I showed in the beginning, for the global state, for everything. And this is kind of the history, so we are not the first ones to do this. I think the most elegant initial idea came from Page and Wouters in 1983. They did this without interaction, and they come basically from quantum gravity, published in PRD. And with interaction in the context of quantum gravity, then there was Halliwell and Hawking took this up, and Kiefer, and we did this in 2000, not in the quantum gravity context, but for innocent normal quantum system, semi-classically. And now there are more recent accounts of that. In quantum science, they don't care that the time operator doesn't exist. So this is typical, I would say, bitching about this, that for this new development. And we published this last year, now finally, after 40 years, how you can include interaction in this approach. And I think people have tried this for a long time, and Sebastian was really lucky or good enough to find a solution. I will tell you about this. So how does this work? What's the idea? This is the invariance principle which accompanies each time-independent Schrödinger equation in the following way. So let's say you have a Hamiltonian and the total energy, and that's then the eigenstate. That's our global state of the universe, of system and environment. You can exponentiate that. And of course, since this is always zero acting on that, you can multiply it by any kind of complex parameter, and this will always give the eigenstate back. And this I call the invariance principle. And now I basically formulate the total Hamiltonian as one of the system in its Hilbert space, one of the environment in its Hilbert space, and a potential which lives in the joint Hilbert space and couples the two. So I assume, because I've constructed in this way, that the environmental and the system Hamiltonian, of course, trivially commute. Now I can construct in 2 lines the solution of the time-dependent Schrödinger equation. Not the time-dependent Schrödinger equation, but the solution to it. That's the trick. So what do I do? So if we assume, and this is what Page and Wouters did, the interaction is so small because the environment is so big that we put it to 0 right here, then of course I can decompose here the sum of the 2 Hamiltonians appearing here into a product of the exponential, into one for the system and one of the environment, because they commute. And the only thing I have now to do is basically I have to multiply from the left with e to the minus lambda h system, and I get this relation. And you see already on the right-hand side, we know this, that's the evolution equation, kind of, for our wave function. But this is still acting on the global state. And of course, what we do now is we project our global state onto some, as I said, conditioning state of the environment. This gives us kind of an initial condition for our system, whatever different conditioning state of the environment we take. So from the left, we do it like this. And this we simply call then, the state of the environment, which is tagged with lambda. We don't care about this. But on the right-hand side, we can, of course, take this by the exponential here because it's not acting on the environmental state. That's the system Hamiltonian. And we get here a wave function of the system. And now we simply define that this projection here is basically the system wave function as a function of lambda. And if you compare this from here and here, you see that this wave function as a function of lambda in the system is e to the minus lambda h at the initial point. That's the solution of the time-independent Schrödinger equation. I've never used the time-independent Schrödinger equation, or time-dependent one, sorry. But of course, I can take now the derivative. And if I take the derivative, trivially, you get the time-dependent Schrödinger equation. So now you know everything. And if you think about it, it's not so trivial. Because first of all, for the whole thing to be non-trivial, this global state must be entangled. Otherwise, your systems completely separate and you go back to the initial point where the global system is the environment system or the whatever. Yeah. So they must be entangled, and you have to demand this if you do not introduce interaction. Second thing, that's the observation. The system state is selected through the environment, which is kind of interesting. And the third thing is, of course, you realize that the change of the system state is compensated by the evolution of the environment. So together, nothing changes because it was our original starting point of the global state. It's exactly constructed in that way. And that makes this relational meaning of time. Yeah? In the relation of system environment, something changes. If you put them together, nothing changes. And now what is very interesting for this relational time is the, oops, oh yeah. Could you put this back? Sorry, put it too long. So the way I constructed it, without a potential, there's no need of ordering of time. So because it's only pointwise defined for each values of lambda. So it doesn't evolve from past to future. It's whatever it is, pointwise here. And only if you say this is continuously dependent on lambda, maybe through a potential or something like that, then of course the derivative and the time-Schrödinger equation is well defined. But it gives you a chance to have disorder in time if you wish. So far no interaction between environment and system. Now let's include the interaction, the V here, on a full quantum level. That means we take now again the projection. We know already how we do this. So this is now the full Hamiltonian from the left projected on chi on the global state. And we use now this projection. We already know the evolution with the environment. And here we add basically a phase, which we don't know yet. This phase could be complex, we will see, but it's just a phase added. And now we insert this here, and you see what this does, of course, to you. You can write this now as a derivative of this wave function, and that basically gets rid of the environmental Hamiltonian, minus total energy, that's trivial phase. And it brings down basically for compensation, because it was not there before, this E of lambda here under the integral, this energy parameter, which is dependent on lambda. And this allows me to take again basically our projection state of the environment by all these operators, but of course I'm still left here with the potential. That's the hard part. So because that lives in both Hilbert spaces or in the joint one, and you cannot take this by, you actually don't know what the action on this is. And now comes something which I try to remember for the future. One should always look very carefully what one needs. And we only make use of the global Hilbert space with respect to this, or of the full Hilbert space with respect to the global state. So we only need properties of that Hilbert space with respect to the global state. That means it's much easier to actually formulate projectors, because they only have to be a projector with respect to the global state. And this is what I construct here. So that would be a standard projector. Let's see here, formulated for the system. And now I construct this projector, which is a concatenation of the projector on our conditioning environmental state, followed by a projection on the global state. And then it's normalized by this n of lambda. And this n of lambda is the expectation value of the projector of the conditioning state of the environment chi in our global state. And now you can show very easily, you can convince yourself that the action of this constructed projector on the global state is really a projector. It gives you the global state back. So nothing changes. And that allows us now to decompose this kind of strange matrix element, if you wish. Because you can insert now this projector. It doesn't do anything, right? It gives you this back, so therefore you can insert it here. And then you can show that with this projector, now this matrix element decouples into a Hermitian potential for the system. That's what we want. That's what a time-dependent Schrödinger equation for the system should do. And basically, in addition, a C number, an expectation value in our global state of this operator, the potential, and times the projection on the environmental state. And then I really can get by here my environmental state, and I have my system wave function. And of course, you realize that this will give me the time-dependent Schrödinger equation. So this Hermitian potential is very simple. We just symmetrize that, right? This is here, and then symmetrize it. So that's Hermitian. And then we have subtract this again, and that gives actually the C number. And of course, now you can guess why we introduced this phase. We simply say we compensate the C number by this phase we've introduced, so it doesn't appear in the end. And therefore, we get, if we put everything together now, the time-dependent Schrödinger equation with interaction for the system. And it carries this kind of Hermitian potential here. That is what's left from the global interaction between system and environment. This is nice and formally very good, and this gives you an idea how this looks like. So this is a two-dimensional solution, let's say, of some wave function. And of course, if our environmental state would be something like periodic here to imitate a clock, then you would get snapshots, which gives you the time evolution in your coordinate of your wave function. It changes here, yeah, from the globally time-independent wave functions in 2 dimensions. That's kind of the idea. And of course, now we don't have to demand anymore that the global state is entangled, because it's an eigenstate of an interacting system. It's automatically entangled. All right, so what do we observe? This phase in general is complex, and this expectation value of basically the potential times the projector. And this allows for loss and gain between system and environment. And this Hermitian time-dependent potential for the system, what I put up here, is the most awkward object you can think of, because it is non-local and depends on the conditioning as well as on the global state. And this happens if you do what? If you have full quantumness, because I did not make any constraints or condition on the environment. I could just have exchange system and environment. So they're totally equal. That's, of course, not what we understand on environment. Environment is big, and so system is small. In some sense, there's a certain asymmetry. This we have not exploited yet. So this is, as I said, the extreme quantumness or extreme quantum case. You can still separate it, but it has a price. It's not very useful. Maybe it will make our quantum people happy who do basically quantum science. Yeah, you will find this in this letter here described. It doesn't take very long to derive it, but it takes a bit to think about it. And of course, just as a side remark, this is now of really topical interest in the context of quantum light, where people try to have not classical light, cosine omega t, but really quantized light. And this is then entangled with the states of matter. And with that kind of approach, one can actually have some insight there. So, yeah, photons. So how do we break the equivalence of quantumness of the system and environment? So we can think of, so the environment is large. How would I translate this in this context? One way to think about this, a simple one, is to say, so if the environment is really very large and robust, then essentially the interaction will not change its states. So that means that the potential, the global potential, and this projector on an environmental state, the commutator vanishes. If this is the case, you get a real phase. So no longer, really amplitude exchange, no dissipation or whatever. It's just dephasing, if you wish. And the local time-dependent potential emerges, which has a very simple and elegant expression. It's the expectation value of the global potential in this conditioning environmental state. That's it. And of course, now your different initial system states come through different global states, which makes a lot of sense because they will be incredibly degenerate, these global states. So you have lots of choices there. And another possibility is, as I said, we did this a long time ago, treating the environment semi-classically. There the idea is then you kind of say, I basically have my entangled wave function, the system as it was, let's say eigenstates of the system. And here I make the ansatz of a semi-classical WKB-like wave function, amplitude. And here the phase, that's the action, energy-dependent action. And the argument is here, of course, the environment energy in this channel. That's the total one minus the system energy. And now assume, of course, that the total energy is much, much larger than the system energy in each channel. And if you do this, I don't go through the derivation, but the important point is you can Taylor expand now the action about the total energy. And dW action by dE, you know this from classical mechanics, is time, right? By basically dimensions already. And that gives you then time times the energy difference in your system channels. And then you end up basically with a representation of your system Schrödinger equation in a matrix form in the basis of eigenfunctions of the system, where the interaction are then matrix elements. And these coefficients here, which are now time dependent, they are nothing else but basically the derivatives of your amplitudes of the semi-classical environmental wave function. So that's also a way to do this. But there you wash away many things because you make semi-classical approximation, and it's only first order H bar, of course. Yeah, but this kind of idea of relational time without or with limited interaction is much more general than you would think of. Or maybe if you think about it, you will realize it. For instance, many of us, at least me in atomic physics, all the chemists, we deal with two-body forces, Coulomb force. Yeah. So we know that always the center of mass separates. There you go. So the center of mass gives you a clock, defines always an environment for these systems. So any symmetry, in a way, will allow you to split this already. And one part is then can provide the clock for the system, if you wish. And now comes, of course, the transitions, not so elegant, to temperature. I mean, the center of mass can be thought, if it's very degenerate, you have many systems, it can be thought as a gas of free particles. Center of mass motion is free, yeah? And then, of course, we know this is a heat bath. And then the idea is, of course, or the question, can we maybe derive statistical dynamics or statistical mechanics for the system from relational complex time? That's now the second part. And that might be, in a way, more natural, but also much weirder, as you will see, because now we really need very, very, how to say, topical quantum properties of our wave function to do that. So we come back to our invariance principle. As I had before, we ignore the interaction once again. But now, of course, we have to do this for the density matrix. So here's the density matrix of our global state. It's a pure state, of course. And then we multiply from the left and the right our invariance principle. This is now lambda star, because lambda can be some complex parameter, time and temperature, if you wish. And now with the invariance principle, remember, I can kind of write this exponential as a product in the system and the environment. And again, I can reshuffle the exponentials on both sides because of this property and end up with a system density in complex time, which reads like that. That's a normalization we always have. So this is here lambda h, and here's this lambda star h. Okay, so far so good. And now this is the most important transparency, which requires thinking and not derivation. And it's also therefore a bit difficult. Therefore, it has a blue background. So we have now to think, how is our global state related to temperature? I mean, in the end, we want to derive temperature for the system, but what does the global state have to do with temperature? And we know this is invariant under this invariance principle. So that means if we take simply the trace at initial condition 0, which is infinite temperature, yeah, then this global state, basically this trace here over the environment of the global state, should represent infinite temperature. So that means also the global state has to do something with it. It's totally entangled. And now the question is to you, does a pure state exist which resembles an infinite temperature scenario? What would that be? So that means basically you have probably also infinite energy, and that means you can spread your system over the entire Hilbert space without any limits in a homogeneous way. There's no differences. Such a state exists. That's the maximally entangled state between a bipartite system, between system and environment. That means now, so a hypothesis is we should use as the global state a maximally entangled state, which is, as I said, completely delocalized. It looks like this. So you all know you can decompose basically a state living in two Hilbert spaces as a sum over product of wave functions, where each of these wave functions here is a basis state in the respective Hilbert state. And nothing prevents us from choosing eigenstates of the respective Hamiltonian of the system here and of the environment. And normally, the Schmidt decomposition would, of course, give you here finite coefficients, real ones. This is then general, we can always do this. And now what we postulate is that these coefficients are 1 to have a maximally entangled state, to not discriminate between any kind of component at infinite temperature. If we do this, we are done. So that means we have now constructed statistical mechanics. Why? So this, I should mention this. Probably some of you know Zurich's decoherence theory. It all comes out what he actually said. So this kind of Zurich's invariant state, the maximally entangled state. Don't have time to talk about this, but it's also before, I mean, the expectation value, if you have the weak interaction with the environment, this expectation value of the potential in the environmental state, these are basically pointer states. That's the same math in the end, what Zurich used at pointer states for describing decoherence. Anyway, so now we are here. We have our maximally entangled state, and we trace over the environment. We insert this here, right? We trace over the environment, and that gives basically the system density as a maximally mixed state, right? The maximally mixed state is unity. This is what you need to construct a canonical ensemble. And now we simply insert this here. And of course, this gives us directly the canonical ensembles, because these are eigenstates of our system Hamiltonian. The imaginary time propagation drops out because it cancels due to complex conjugation, but I mean the real one, whatever you mean, e to the I lambda cancels, but e to the minus gamma, or 1 over temperature, remains, and this is what you get. So you get really the canonical density, the Gibbs state. So again, only from relational time, and by demanding that the global state is maximally entangled. That's all you need. And of course, then the entropy follows, and the entropy fulfills the thermodynamic relation. That means change of entropy at fixed temperature is proportional to the change of the internal energy. That's the thermodynamic relation. And we have not used or counted the states in the ensemble, and we have not maximized the entropy. That all follows. Only by having a maximally entangled global state, nothing else in relational dynamics. And you can in a way say it's the same thing from which we constructed the time-dependent Schrödinger equation for imaginary time. All right, so that means complex relational time evolution with a maximally entangled global state means equilibrium statistical mechanics for the system. And as I said, the counting of states or maximizing entropy is not necessary. And that kind of, how to say, is very satisfying for me, because I never understood as a student why the wave function is an ensemble. And then in statistical mechanics, you have to build ensembles from ensembles to average over them. I never understood this. Not necessary. Okay, so this is an attempt to kind of visualize maximal entanglement. I had to talk to the academy in Saxony, where there's historians and whatever and so on, how to explain entanglement. I still don't understand it myself. So that's, you can tell me in the coffee break if you have a better idea or if this makes sense to you. So let's say we have like 3 pairs here of environmental and system wave functions. That's the environmental wave function. That's the system wave function shown here. Yeah. And then, of course, you have the sum. So they're entangled. And the entanglement now, if it's maximally entangled, is kind of really putting to the connection between those, because it's totally democratic. So it doesn't take any notice how these pairs are different. It just goes to the connection. The maximally entangled state is, of course, a pure global state here. Entropy is 0. And we can also now form, of course, another state of system environment, where there's also information in the system as well as in the environment. And this I try to signal here by these triangles pointing to the wave functions directly. Now the entropy is larger than 0 because this is already a partially mixed global state. Now do the tracing, yeah? Basically get rid of your environmental state. So what happens is here, if we do the tracing, we get rid of our environmental wave functions and of course of the connections. And you see the system states do not have any connection anymore. Maximally mixed, there's just no relation. But if you do this here, then the connection will remain among the system states. That means if you have not basically a maximally entangled state to begin with, you have some finite entropy, then we will also have some finite entropy after tracing. While the S equals 0 maximally entangled state will take you to a maximally mixed state. And that's the funny property we need to construct statistical mechanics. That's the only property one needs, but that one really needs. Yeah. Now I'm almost at the end. So this is to try to kind of summarize and give you again this logic of relational dynamics or physics. So you have the time-independent Schrödinger equation for your global state, an eigenfunction. And this is connected with this invariance principle, which is, of course, then very important. And then you split basically your Hamiltonian into a system and the environment, and they evolve relationally with this parameter lambda. And now if you take this parameter as time-like, E lambda, lambda real, and you project onto a good conditioning state of the environment, or if you take this parameter, in this case, as imaginary, you can actually leave it complex. It doesn't make a difference. And you trace over the environment, then you get the solutions without going to the differential equations or the conditions which we normally use to derive these solutions. So you get the time evolution for the system, or you get here the canonical or Gibbs state distribution of the equilibrium state. And from that, of course, you can derive then what we normally use as a starting point, the time-dependent Schrödinger equation, or here your thermodynamic relations. And so this says essentially what I said in the beginning. That's the proposal why time is derived and only comes about in the separation. And the fundamental property is a time-independent situation for everything. And now to the very end. So once you really dwell on this, it doesn't let you go, this idea in your life and so on. This is what happened to me. So I give you a few examples. You can think it's crazy. It's not this kind of sacred ecology from yesterday, although it looks like it a bit. Anyway, so relational time in real life. The first one is still kind of reasonable. So of course, if you think about how we have measured time for centuries, since we measure time, it is always comparing spatial motion, right, of planets and so on, versus motion we want to actually bring time to. And that is exactly this relational kind of idea. And even now, our atomic clocks are kind of vibrations, oscillations, which is also not really in time. So it's also, in a way, a spatial motion, if you wish. Now, on a more personal level, if you're totally fascinated by a book you read, then time flies, right? You look up again and it's 2 hours later and you think maybe 10 minutes have passed. Why? Because you have basically become unified with your object of interest. And during that time, there's no time for you. Of course, externally, it still kind of goes on. The opposite, if you're bored, time is endless. And then I told a few of you that already, so I tried to shop around a little bit in literature and other fields of phenomenology. There's a famous developmental psychologist, Jean Piaget. Some of you may know that, him from last century. And he tried to basically empirically find out how we as humans learn concepts like time and space, especially for kids. And he found out the following. So he tried to investigate when do actually kids have a reliable idea of time spans. In the beginning, they don't have this. We all know when we have kids, or maybe remember ourselves, probably not so well. Because you say, yeah, no, we go on vacation, 2 weeks from now, and an hour later, your daughter asks you, when do we go on vacation? And it turns out that also people, and I think I asked this is also true in Mexico, it's definitely true in Europe. In the beginning, kids don't say I, they say their name. They say, Anna does this or that, or so on. And now you can guess what Piaget found out. So kids have a reliable idea of time spans when they start to say I. Relational time, right? If you can separate yourself from the environment reliably, then you have an idea of time, then time makes sense. Yeah, time in dreams, we all know it goes totally crazy. Again, you don't have a separation of your individual consciousness there, and then time goes crazy. And the last thing is, of course, time in myth and religion. I will not dwell on this, but if you know different kinds of religions, always this concept of being separated somehow and being reunited with something and then time ends is very widespread. Okay, in Christianity, we are here in Mexico, you can say in the paradise there's no time, and if you're expelled, Adam and Eve are expelled to earth, then you can read in the Old Testament that you have the kind of generation of fathers. That's very important there. That's nothing else but introducing time. Anyways, so much for something which you may remember, and with that, I thank you for your time.
Thank you very much for this really nice talk. Are there questions?
So if you think about time in a context of general relativity, time is never really defined as there's reparametrization invariance. So that's my first question, and how you think about that in your context. The second question is, if you have the entire universe and you want to define time as say the separation of everything, the redshift. So how does that work in yours?
Yeah, so these are things we start to think now about, but unfortunately I'm not so skilled in general relativity and so on. But my initial idea would be that to some extent, general relativity, I don't know, but it is special relativity, it's a representation problem. So I could take still my abstract states and project them onto something which corresponds to a Hamiltonian, which makes the coordinate system. Here I can trivially do this free motion, what I have, center of mass motion, that's momenta, right? Then I have a coordinate system, then I have psi of p for the system. Now, of course, I could take a relativistically evolving particles or free particles, and then I would probably get at least special relativity from that. For general relativity, I might need your help, Jack, so I don't know yet.
Yeah, thank you for a very nice talk. This parameter, capital lambda, you either chose to be imaginary or real. But if I just take a complex parameter, do you get something like Lindblad equation or something like that?
Yeah, so that's on the program to derive this, to derive open systems dynamics and basically the Lindblad equations. And what you also, of course, can think of, you can take a path in this complex lambda plane. And this might give you quite interesting results for eigenstate thermalizations and things like that. Yeah, so that's on the agenda. Okay. And I think what turns out is, so what is very nice, and I was very excited in the beginning about it, because it's all well defined. We don't have trouble that something doesn't converge because the global state is there. But there's always a conservation of difficulty. If you split things on this dividing line, things gets really complicated, and people have realized that in many body physics a long time ago with trace class operators and so on. So there, I think it catches you again. But nevertheless, so that's, yeah, you're quite right.
Thank you.
Just partly as a joke, could you actually travel backwards in time? Was this without my explain?
So this depends on this complex parameter. I mean, this phase, right? Which, if you have really interaction, is complex, and which actually breaks the direction of time. And then I guess you would have to invoke something like thermodynamics, second law of thermodynamics, to prevent this. Yeah. But in the end, so far, this doesn't give you anything more or less than our standard time-dependent perspective. And so modest as I am, I would say this is very similar to, having the Earth in the center and switching to the sun in the center. In the beginning, there was no difference. I mean, they could describe this equally well, a bit more complicated. But these kind of questions, of course, also kind of, move us and make us think, and maybe something follows from that. And can only encourage you also to think along these lines. It's fascinating, yeah.
What would be the meaning of the of the environment there? Is it something fundamental, like because I can imagine that the central system would be essentially the universe, right? Or do we need another big universe in order to get this? Because this would be like the time for everybody, or it would be what type of environment would you get? And
Yeah.
and another question, if you do not take a maximally entangled state, probably some intermediate entangled state, would you also be able to influence the temperature of the final Gibbs state and stuff like that, in maybe even time? Maybe this is also where the Lindbladian comes from also? I don't know.
Yeah, so for the second question, that's actually quite interesting. We have even proposed that one could probably construct, like with traps or so on, and cavities, a situation where you have not maximal entanglement, and then study non-ideal thermodynamics in that way, which then relies on a not maximally entangled state. And maybe one gets some systematic consequences of that. Quite true. And the other question, I mean, you saw that we have derived this completely generally, just two systems separated, and then it gives a very complicated time-like interaction, which is not so much time-like as we're used to it. This is really crazy, non-local and blah, blah, blah. And only if you make one system much larger in one another way, like an environment, then you get back what we kind of perceive as time. So I would say whenever it's asymmetric enough, and it's fine. And honestly, back then in 2000, we tried hard to find basically something you could prove experimentally that this approach makes sense. And that's the back action of your system on the environment, which you neglect. Semi-classic, you see, it's like Born-Oppenheimer approximation formally. So you see this directly. And if you work this out quantitatively, it's totally impossible. So you would have some ingenious ideas, somebody indirectly to measure that, like shelved states in the old days or so on like that, where you indirectly measure maybe. But if you really measure, like we measure, then it's almost basically already classical, and the back direction is so small that you cannot detect it. That means we live, our standard situations are really in a time-like environment. I would say you probably have many examples by now in quantum optics where time doesn't make sense. And one old example, this is also from my graduate days, you are too young, but this was Paul Demuth when they actually could trap a single atom for the first time, which was not in the Copenhagen interpretation. And then Demuth had this ingenious idea to have like a 3-level system where you drive a transition, and then you get basically bright and dark intervals. And you repeat your experiment, it's totally fine, but you can never repeat these jumps. I found this, I didn't understand why this is not more of a crisis for natural science, because it's really, but, so this of course means a situation for us where the time doesn't make sense, because you couple two small systems. It's two states in the electron, and it's maybe 0 or 1 states of photon in this transition, in the spontaneous decay from this intermediate parked state. This you drive, but that's not the one you observe. You observe when the electron gets parked and the spontaneous decays back in the ground state, and then it's fed back into the cycle. And now, so how do you get actually time in that? You average over small spans. And that is kind of a way to make statistically your environment large. And then you get the lifetime of your intermediate state. That I find this very consistent with this idea.
Excuse me, could your formalism or this framework throw some light on violations of Bell inequalities? I mean, I'm just not joining two strange subjects. There is an element of time, because the problem is with any picture of causality, and causality does involve time. And you cannot imagine these correlations being caused unless they're non-local. So could your approach help with that?
We are trying this right now, but it's not yet decided. So the idea would be to have basically in a timeless description, time-independent observables, which would commute. So you would have one in the environment, one in the system, but this is totally consistent with what you normally would measure. And then there So the sequel doesn't matter, right, in this expectation value of a density matrix. But once you introduce the splitting in system and environment, it matters. So that's the idea along which we try to pursue that, but no results yet.
Yeah, you have two questions. One is also regarding this, what could do regarding Lindblad, this stuff. But for example, not Lindblad, going beyond, for example, with Redfield kind of stuffs, with memory. This will be, I think, also a hard task to get, because now you rely also on something which depends on the past, at least. Or how could you think you could approach to this?
I mean, yeah, so memory, of course, says that you rely on the past.
Yeah.
But that means not only onto your immediate past, but on the history, right?
Yes.
And I think this is included. This comes through this kind of complex phase, which is very innocent, this e to the I integral lambda, d lambda of e, where I said, this is really complex if you have full interaction, and that gives you the access, yeah, to all you need in a way.
Okay.
It could even probably contain something like dissipation fluctuation theorem if you do this the right way in a linearized interaction. But this is the full solution if you wish, because it comes from the global state under no constraints on the interaction of system and environment.
Now the second is for this maximal entangled global state, when you get the thermalization for your system. Now, what if you take a system as a central system that you're focused on, which is also interacting with something else? So, you know, you will have to lose certain entanglement with the rest, with the environment, to get entangled with your other local system. So at the end, that would mean that you will probably end up in not the traditional Gibbs canonical states, but something different. Will this allow that?
So you're thinking of a hierarchy of systems where
yes,
one is coupled to the next.
Thinking also on sort of monogamy of entanglement, that you cannot just entangle the.
I mean, yeah. So if you do this basically pairwise, you probably can still handle this. If you would do this all the way, then you have multipartite entanglement, which is, for me, a nightmare. I wouldn't really know how to deal with this right now. But in general, this was already the question. Of course, you could think of thermodynamics, which is a variant of thermodynamics, which is not the one we have. And now it's well defined via non-maximally entangled states. This will still give you thermodynamics, you can derive all, but it will give a different result, and you know why. So it's not uncontrolled. And the first thing would be to design an experiment, as I said, probably with cavities or so on, where you really specify this global state, but not maximally entangled, or you can define a little bit the degree of entanglement, and then see what kind of thermodynamics results. Yeah.
Okay.
Are there further questions? Okay, I have one question. So it's about the thermodynamics or statistical mechanics. So, and it's a conceptual question. So you say that you can you can arrive at the canonical ensemble, but what does it really mean conceptually? So if I am in the system and I only have, at one time, I only observe one configuration of my statistical ensemble. How can I understand that you get the ensemble at once, say, the canonical one?
No, first of all, what this means, if you think of it like a time, like a propagation, now in imaginary time, but for an ensemble, that means it takes you basically from one equilibrium situation to the next one. That's what the solution means. Yeah. So you define it by this global state, and the interpretation is that this is at infinite temperature, and then directly you can, via this result, translate or can answer what your system looks like at a finite temperature, at any finite temperature. That's kind of the interpretation, and always it always obeys, of course, the maximum entropy principle automatically. So you don't have to construct this. So what this imaginary time propagation means in that context is taking your system from one equilibrium situation to one at a different temperature.
So this rho thermal is really a reduced state then.
Yeah, yeah.
Thanks. Any further questions? Okay, then thank you very much, Michel. And one quick announcement. The photo, we have to repeat, this will be done at the end of the coffee break, not right now. So please be there at the end of the coffee break. Or be still there.
Probando, probando, probando.
Que ya tienes la presentación de Mauricio Torres.
Probando, probando, probando. 1, 2, 1, 2. Probando, probando.
Probando.
No se puede poner aquí. ¿Será que? Mejor que puedo usar las manos.
Sí.
Ahorita. Muy bien, muy bien. Oigan, ya vamos a comenzar la sesión, por favor. Vamos para adentro. Gracias. Sí.
No, no está bien. ¿Me escucha? Sí. Lo uso.
Good morning, everyone, and welcome to the second part of the morning session of today. So we have now Professor Lea Santos from University of Connecticut. She will talk about dynamical manifestations of many-body quantum chaos and self-averaging. So please, Lea.
Okay. So first, I'd like to thank the organizers for the invitations and you all for attending the talk. So the results are, I don't know, can you hear if I move around or should I hold? Okay, maybe I should hold. Okay, so the results that are presented here were obtained with Jonathan Torres, who is a professor in Puebla, previous postdocs Mauro and Thalia, current postdoc Isaías, and students Edwin David. David should be here in the audience. So I'll tell you how we can detect many-body quantum chaos through the dynamics of complex many-body quantum systems. And also, what are the problems that we find when we are trying to do that? In particular, the problem lack of self-averaging and how we can avoid these problems. Okay, but before I start with this, let me just give you an idea of the systems that we have in mind. So these are systems of spins half. So what we have on each side here, so these are lattices. So on each side we have a two-level system. So I'll be using the language of spins. That's why you see Pauli matrices here. But if you prefer, you can think about it as the presence or absence of a particle. Okay, and these models are used to describe several real experiments. For example, experiments in NMR. What they do there, apply a magnetic field, so the spins get aligned, turn it off, and then they study the relaxation. They are also used to explain or to model the experiments with cold atoms in optical lattice. So they shine lasers in opposite directions, so you get these standing waves, and then with these standing waves you can trap the atoms to a specific position. So these are like crystals of light. You prepare an initial state, and you can let it evolve. So these are systems that are highly controllable. It's also used in experiments with ion traps. So with these electric magnetic fields, you trap the ions to arrays, and they can be well described by spin half. These are all systems that are highly controllable, long coherence times. So, as I said, we are going to detect many-body quantum chaos. For an audience in Mexico, I don't need to dwell too much on that. Now you know what I mean by quantum chaos. I mean spectral correlations as in random matrices. So the eigenvalues of random matrices are strongly correlated. If you study, for example, the histogram of the space in between neighboring levels, you get the famous Wigner-Dyson distribution. So if our many-body quantum systems present a Wigner-Dyson distribution, I'll just say that the system is chaotic. On the other hand, if the eigenvalues are uncorrelated, we'll get the blue curve, the Poisson distribution. Now, not everybody accepts this definition. If you want to discuss that, we can talk about it later. That's what I'll be using. If you don't like this definition, whenever you hear the word, the term quantum chaos, forget about it and just think about spectral correlations. Okay? Okay, but that level spacing distribution only detects short-range correlations. We want a more complete quantity that can detect also long-range correlations. So I'll be talking about the spectral form factor that Jack already told us about on Monday. So what is this quantity? Now it's the Fourier transform of the two-point correlation function. So you see now we can detect long range because we have all eigenvalues here. T here is for time. So when time is 0, this quantity is 1 because I normalize with the density or with the size of the matrix. No? So no matter which size of matrix, it will start at 1. At very long times, it will reach a plateau, which we are indicating here with these horizontal lines. What is this plateau? No? So you can see it by splitting this double sum into the terms that where alpha and beta are different, and the other term when alpha and beta are equal. So this is the point of where we reach that plateau, is the saturation. Now why? Here we just have sum of cosines. Now at very long times, this thing averages out. We just have these small fluctuations. Okay, fine. So now what do we have in between? 1 and the saturation. Well, sum of cosines, this thing is going to decay. Now, if we have eigenvalues that are correlated, you see that we go below that saturation line and go up on this ramp. So this feature that you're seeing here, people now are calling it slope deep ramp plateau structure, very long term. Some people just call it ramp. No? It only shows up if we have these spectral correlations, as in random matrices. But instead of using this long term, and ramp was a term that was introduced in high energy physics, and now it's everybody's using, also in condensed matter and so on. Instead of this term, I'll just call it by the name it used to be known, the correlation hole. So the correlation hole was studied, for example, in this paper back in the 80s, where they were trying to describe, study statistically the spectrum of molecules. The problem with molecules is that you don't have good line resolution, not as good as in nuclei. So you can have some overlaps. So the idea is, well, let's do the Fourier transform to try to detect these correlations. And the term was used in many papers in the 80s, in the 90s, some papers by people in the audience, Tamás, François. So to give credit to all these people, I'll keep using this term, and also because it's much more informative than just a ramp. Okay, but instead of the spectral form factor, I really want to study dynamics. So I'm going to look for a quantity that gives really information about dynamics. Now, the spectral form factor is just an analysis of the spectrum in the time domain. Instead, we will look at the survival probability. Very simple quantity, just the overlap between the initial state and the evolved state. If we project this initial state in the energy eigenbasis, we get these components, which you are seeing here, the components of the initial state. And on top of that, we have the phases with the eigenvalues. So you see that this is just like the spectral form factor. It would be equal if I had an initial state where all components were equal. But this is not the kind of initial state that is physical. No, we want initial states that can be prepared experimentally. So, such as these kind of states where on each side the spin either points up or down or where I have or do not have a particle. These are the states that people prepare with cold atoms, with ion traps. Okay. All right. So we started studying this quantity to analyze the correlation hole with Jonathan in the context of many body localization. So let me tell you a little bit about this problem. So here we have a Hamiltonian for a spin half. This system is in one dimension. This first term here, what it gives us is the Zeeman splittings for each side. These HNs are random numbers, so randomly distributed. So we have different Zeeman splittings in this range. In addition to that, we have this term of interaction, the easy interaction, and this other term, x, x, y, y, this is like a term of kinetic energy. It moves the excitations along the chain. Now, if we forget about the term of interaction, we have just hopping and on-site disorder, we have localization. No matter how small that disorder strength is, you have a localization, meaning the eigenfunctions decay exponentially. This is the idea of Anderson localization. Okay, so we trap the functions. Now, when we add interaction distortion, things become much more complicated because this interplay between the interaction and disorder brings the system into the chaotic regime. And chaos is usually associated with spread, delocalization. So when the disorder strength H is of the order of the coupling parameter, you will see nice Wigner-Dyson distributions. As we increase the disorder, and if you're dealing with a finite system, you will see that this will get more and more deformed until you get to the Poisson. Well, this was studied like 20 years ago. In parallel, if you look also at the structure of the eigenstates, what you're going to see, the things also change. So this is one of the eigenstates. We are writing in terms of these spin configurations because we want to study localization in real space. So if I have a delocalized state, we'll have many, 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 many tiny C's participating. So if I compute the participation ratio, 1 over those components to the fourth, this will be very large. If we have contributions of just few of these states, participation ratio is small. Okay, so as we increase the disorder strength, we go from Wigner-Dyson to Poisson. You see that the value of the participation ratio goes from a big number, delocalization, to a small number, localization. Well, this transition you will find for sure if you're dealing with finite systems. This is something that we did 20 years ago. But the question nowadays is whether this will persist as you go towards the thermodynamic limit. Now, can we really talk about a transition? And there is a lot of controversy there. One of the reasons is we are dealing with enormous Hilbert space, so doing scaling analysis gets really hard. I'll tell you about another problem later on. But anyway, coming back to what we are doing with Jonathan. In that region where we have good chaos, well, we'll have, of course, a very nice correlation hole. As we increase the disorder, the hole shrinks until it disappears. And, of course, because we are killing the correlations. And that's what you're seeing also in these figures. So we studied the depth of this hole, but we also studied the time where the ramp starts. So this time is known as Thouless time. Okay, so you see that as I increase the disorder, this time increases. And we studied how it depends on the disorder strength and increases exponentially with the disorder strength. Okay, so this is a result that we did with Mauro, and then Prozen and Leo Widmer also confirmed the same thing. Now, it's growing towards this green line. This green line is the Heisenberg time. Now, it's the largest time scale of the system. It's the inverse of the mean level space. Now, it's the time to reach the plateau. So the question is whether we are going to meet. In finite systems, yeah, it does. But the question is whether they will meet in the thermodynamic limit to talk about localization. Okay. All right, but this is just to give you a short introduction. The idea then to detect many-body localization or spectral correlations in the dynamics is just to try to detect the correlation hole. Now, the problems with that. So there are three problems that I want to discuss with you. The first one, I'll be very brief. The first one is that the survival probability is a non-local quantity. So this could give extra trouble, no extra work for the experimentalist. We know that they can do this now, but what we did with Jonathan was to try to find for a local quantity where we could still see the correlation hole. And the quantity that we picked is this one. So it's the spin autocorrelation function. So what it does is to measure the magnetization times zero, no? How close the magnetization times zero is, or versus magnetization at time t is to the initial one. And we average over sites. And you're going to see the correlation hole, the same thing at the same time scales, because correlation hole is just a property from the spectrum. No? So it doesn't matter the quantity, it will show up at the same time scales with the same features. Okay, there is more to this story. You can ask me if you're curious, okay? There are some issues with the spin autocorrelation function. Okay, problem number 2, we probably already anticipated. The correlation hole shows up at very long times. You need to give time for the dynamics for it to resolve the discreteness of the spectrum and then detect if these eigenvalues are correlated or not. So it will happen at very long times. So you would need extremely long coherence times, and the values of the quantities tiny. So you cannot do this with current experiments. How we solve that is trivial, okay? Is you just look for the smallest chain where you can see the correlation hole. But before I show to you this the results for the small ones, let's discuss a little bit time scales. There are lots of things to be done with respect to non-equilibrium many-body dynamics. No? I'm just going to tell you one of these aspects, but there are many things to explore and things that we've done as well. So to talk about the time scales, I want to discuss here just the time scale for the correlation hole. And we are going to compare the evolution of the survival probability for 2 scenarios. One is let the survival probability evolve according to random matrices. No, matrix completely filled with random numbers. Completely unphysical. Why we do that? For the same reason that Wigner was using these matrices to study nuclei. No? We can get analytical results. We know that how the levels are correlated. There are books about these correlations. We know that the eigenstates are just random vectors. And we compare, so this gives us analytical results that can guide us on the study of real systems. So I'm going to show results for this disordered spin model that I've been telling you about, starting with initial states like this. But this result here is general for any system with two-body couplings. Okay, so let's start with the random matrices. I said we can get analytical results. So this is the equation that describes the evolution of the survival probability for the whole time, no, from perturbation all the way to saturation. So this bar here is indicating the saturation. This B2 function is the two-level form factor that we find in Mehta's book, for example, and it describes the correlation hole. What comes before is described by this term, and I'll explain to you in a second. If we compare with the spin model, well, at long times the behavior is the same. Saturation, of course, and the B2 to give us the correlation hole. What changes is the short time behavior. And where do these things come from? Well, this short time behavior is determined by the energy distribution of the initial state. In the case of full random matrices, we have a semicircle. In the case of physical models, we have a Gaussian. Yeah? So the Fourier transform of the semicircle is what gives us this term here. This is the Bessel function of first kind. So this is what's describing this behavior. In the case of real systems, you have a Gaussian, so Fourier transform the Gaussian is a Gaussian. Since there are bounds in the spectrum, you also get a power law. Okay, so this expression here is analytical, is shown here in red, numerics is in black. This expression here is semi-analytical. We just took the same steps that we did for random matrix to get this one. So this expression is here the dark curve, and numerics is red. So very similar behavior. Very good agreement. Now, the difference at short times doesn't seem to be so special, but you see that it will change everything about the time scales. Because here, the width, this gamma here that appears in the equations everywhere, this gamma is the width of the energy distribution. In the case of random matrices, it grows with the dimension of the matrix. So it grows a lot. While here, it grows with the chain size, so it's much slower. So this changes completely the time scales. Let me come back to show you. To get to the time where the ramp starts, all we have to do is to see where these two parts meet. No? This one is taking us down, this one is bringing us up, so where they meet. So we get this analytic. For full random matrices, this time is constant. Okay, so this time is constant. We increase in the matrix from top to bottom, and you see the ramp starts always at the same point. In the case of the spin model, you see that this time grows with the chain. The chain is increasing from top to bottom, and you see that this time grows exponentially. And why is that? In the case of random matrix, I start with an initial state that is directly coupled with all possible states, no matter how big the matrix is. So it doesn't depend on the matrix size. On the other hand, for the spin model, the scenario is more or less like this. I start with a state like that. Well, that spin up first is inside 5. First it goes to 4 and 6, then to 3. It goes gradually, step by step. And it has an exponentially large number of states to visit. But it goes step by step like that. So it takes an exponentially long time for this to happen. Okay, how we are going to solve, I already told you. Now how we solve this problem, just look at very small chains. So that's what Edwin and David did. We studied different spin models. We studied survival probability, spin autocorrelation function. So for this spin model that I've been talking about, you see that even with just 6 sites, you can get the whole there. Okay, so that's the discussion about this proposal to the detection of many-body quantum chaos. But we went one step further, and we proposed a quantum circuit to try to detect the correlation hole. So if you detect that in a hardware that is available, that would be proof of experimental, it would be an experimental demonstration. So the circuit is shallow. We put it in one of the IBM providers, and these points is the survival probability. And you see that we kind of see the ramp starting, but then you lose it because of noise. We are improving the circuit, and we are going to run it in one of the ion trap computers where the noise is smaller. Okay, but in the meanwhile, this is a paper from January. There is already a paper available, not PeopleFest. In March is a big group where they detect the correlation hole using superconducting circuits. Of course, they don't use the term correlation hole, but it's the same thing. All right, so this problem is solved. Now I go to the last one, and that's the one that I want to spend some more time with you. Okay, good. So this problem is the lack of self-averaging that I mentioned in the beginning. Survival probability, spectral form factor, they are non-self-averaging. First, I'll tell you what the problems involved with that, and then I'll define self-averaging and explain how we can solve this problem. Okay? So, if you pick just one realization, one initial state, and you look at the evolution of the survival probability, you will get curves like this gray one with these big fluctuations. It can be so big that it can hide the correlation hole. So this is related to this problem of lack of self-averaging. This was discussed already in the 90s in the context of the spectral form factor, many numerical results. What we did with Mauro was to study the survival probability, as you know, it's similar, but analytically, using random matrices. And then we showed analytically in this work that it's non-self-averaging anywhere. We did also analysis for physical models, and things get really bad once you start putting a large disorder. This is the introduction, but now let me tell you what is self-averaging and how we are going to solve this problem, okay? So we'll say that a quantity is self-averaging when its relative variance, no? So the variance divided by the square of the mean, when this thing decays as the system size increases. So this is very good because if you're doing an experiment, that means you increase your system size, you can reduce the samples, so it's not going to be too costly. In our case, if you are doing some numerical analysis, you increase the system size, your Hilbert space grows exponentially, well, at least we can reduce the number of realizations. And if you're trying to come up with a theory, you can develop that theory based on these samples from the finite system. Okay. If this is not satisfied, we are in trouble. In the studies of many-body localization, I told you that one problem is this enormous Hilbert space. The second problem is exactly that, lack of self-averaging. That's what we wrote here. So to get convergence of our results, no matter how big the matrix is, you have to do 10,000, 30,000 averages over 10,000, 30,000 samples. And so it's really costly. If you don't do that, you may reach wrong conclusions. Okay? All right, so as I said, we studied this quantity here analytically with Mauro. It's tedious work, okay? It's possible to do, of course, but you're now dealing with the square of the survival probability, so you don't have just 2-point correlators. Now you have 3, 4, connected, disconnected, all combinations. But Mauro was very patient and he got the analytical expression, which is shown here. Okay, so this is the survival probability increasing from top to bottom. This is the relative variance of the survival probability. Now, the matrix increases from bottom to top. So that means the relative variance is increasing as the matrix increases. This is just the opposite of what we wanted. And at long times, this thing is just constant. This is also bad. We want it to decrease. Okay? So how can we solve this problem? How can we ensure self-averaging? So the idea came from a paper by Adolfo del Campo, which is a very nice paper where he studies the survival probability, but in an open system. The else that they used here is just the Hamiltonian. So this is a scenario where we would just have dephasing, okay? There are other things to explore. I'll be just telling you about dephasing. And so if you just have this Lindblad, you have an expression for the survival probability. This is the new term, kappa. Here is the dephasing strength. So the survival probability is here for the isolated system, this dark blue. Just one realization, you see the fluctuations there. You open the system. If you open too much, if this kappa is too big, the light color, you destroy the whole. No? If you open the system is becoming more classical. You destroy the whole because the whole is a purely quantum property. But if kappa is not too big, you can still follow the ramp here. And the nice thing is that you don't see fluctuations anymore. You really reduce the fluctuations. So when I saw that, I came to talk to Adolfo and I said, well, let's see if this reduction is enough to ensure self-averaging. So this is what we did in this work. So just repeating what we have. Isolated system, one realization is the red curve, big fluctuations. You open it a little bit, and you see the red curve, the fluctuations are almost gone. The relative variance, that thing that I told you, it plateaus at 1 when the system is isolated. You open, it goes down a lot. So this is all good sign, but still we have to do scaling analysis here. And if you do a scaling analysis, you see that the relative variance does decrease, so we are very happy. So through the environment, you gain self-averaging. Now, this analysis was done just for random matrices, and the kind of initial states here, Gibbs states. So these components are just Boltzmann factors. What we are going to do, what I'll show to you in the next slides, is what happens when you deal with real systems. But there is a nice discussion in this work, and this is really due to the Adolfo's students, which is what do we have when we have an open system? No, it's non-unitary dynamics. When you do averages, you also have a non-unitary dynamics. No? So it's this comparison. So basically, we are gaining the average through the environment. So that allows us to play even with one or few realizations and get these smooth curves. Okay, but what we did next then is to move to physical systems, and then as Isaias, Edwin, and David. So what do we get? Well, this panel is repetition, okay? It's just the random matrices. Isolated is the light curve, dark is the open one. This is survival probability. Relative variance is what I'll be showing to you in the next slides. Relative variance for isolated is plateau at 1, non-self-averaging. You open, oops, it decays a lot. This is the scaling analysis. So we are happy about that. Now we wanted to do this for physical models, but we started by looking at random matrices that put us closer to physical systems. So not just these full random matrices. So one of the matrices that we considered is, before going to physical systems, power law banded random matrices. So what are these power law banded random matrices? You have random numbers in the diagonal. You have random numbers in the off diagonal as well, but as you I need my hand. As you move away from the diagonal, the amplitude decreases. And it decreases according to this parameter alpha. So if alpha is 0, we are back to random matrix. But as you increase alpha, you will reach a critical point at alpha 1, beyond which the system becomes localized. Okay? So if you do the analysis for small alpha, you're back to the scenario of random matrices. But if you go into the localized region, this is the saturation for the isolated. Once you open, it decays a little. It decays a little and no improvement with system size. You see, this scaling analysis is just a straight line. So you don't really get self-averaging by opening this matrix once you move away from chaos. So this becomes more clear with this scaling analysis done for different values of that parameter alpha. So what we are studying is this saturation value, so how it behaves, how does it depend on the dimension. So we are picking this exponent here. In the case of close to random matrix, this exponent is -1. So alpha is small, random matrix, this exponent is -1. When we go to the localized region, this exponent is 0, is the flat line there. In between, things are really bad. Once you reach that critical point, these exponents are positive, so the relative variance is increasing. It's the opposite of what you wanted. This is what we usually expect around critical points. Things get very bad there. You have the states fluctuate a lot. You have multifractality. But what we are showing is that even if you open the system, you're still having this trouble. Okay, so I'm about to finish, okay? Okay, we did this for other kinds of random matrices, the Rosenzweig, port and ensemble, just to show again, things get very bad at the critical point. So that was all to anticipate what to expect for physical systems. When we pick now the disorder model that I told you, in the chaotic phase, everything looks good. This is isolated. You open and the relative variance decays. So if you look at that exponent, the exponent is negative. As you start increasing the disorder, you move away from that chaotic regime, you're losing your Wigner-Dyson, then what you see is you may reduce a little bit the fluctuations, but you do not ensure self-average. You see the scaling analysis show exponents that are positive. So things are really bad there. So if you would look at this result, you would not anticipate any many-body localized space. Yeah. So, but this is all coming from the structure of the eigenstates. As I said, they fluctuate a lot once you reach critical points, and here it looks like throughout this disorder strength. All right, but there is one more point to this story, and then I'll finish, okay? These real systems, if you look at the density of states of these real systems, is a Gaussian shape, right? Which means that chaos and eigenstates that are close to random vectors, so they're all very similar, or thermalization, or ETH, all that holds in the middle of the spectrum, not at the edges. So if I start with an initial state, even though the bulk is chaotic, but if I start with an initial state here, if I open the system, I still do not ensure self-averaging. Okay, so there's two dependence here, initial state and also the model that we're dealing with. Is it a critical point? Is it a localized space? Okay, so that's the idea. So to summarize what I showed to you, we can detect many-body quantum chaos through the correlation hole. We propose that. We have a circuit for that. Some people already did, and the discussion is here. But to do this, you have to play with small chains, which is usually the opposite of what we try to do. Self-averaging is a problem which can be solved by opening the system, but only if you are really dealing with chaotic states, not if you are outside of this chaotic region. And I just want to finish with one message. So by opening the system, we saw this reduction of fluctuations. We use that to study self-averaging, but I'm sure you can find other applications for that. So thank you.
Thank you. Thank you very much, Lea. So is there any question? Yeah, please.
Yeah, I want to ask about improving self-averaging. Is that the same as just adding an imaginary part to the energy difference?
Yes, it is. It is, exactly.
Okay, and you mentioned...
Because it's here, right, Jack? Let me just... Yeah, you see, it's this term.
Okay. And you mentioned other applications of opening the system. In fact, we did it many years ago.
Okay, good.
When we were
should have cited you
solving the Skirm model of colliding skirmions, and then we added artificial viscosity to the equation of motion, which is a technique used in astrophysics to solve general relativity equations. And that's very important to do. And artificial viscosity, you lose energy, but it still works very well to get out the fluctuations.
So you reduce the fluctuations with that. Did you study self-averaging or no?
No, we just use it as a numerical technique.
Okay, very nice. Okay.
I have two questions, I think. First, about self-averaging. There's two issues, I think. One is with respect to the initial states. So you could, say, take many initial states, or you could take a mixed state for the initial condition, and to the system, right? So you can do different Hamiltonians. And of course, one could define self-averaging for a quantity where you take a mixed state as an initial state.
Yes.
And the second question is, even if you have only one realization for one initial state, you could do smoothing, right?
Yeah.
How does it compare?
Yeah, I know. You can do any kind of average that is available to you. So averages over disorder realizations, average over initial states, running averages, combinations of all this. But whenever you do that, the running averages, that's how you ensure self-averaging, by doing this. But here I'm saying I don't need to do any of these things. I pick one realization, and I got this running average through the bath. Yeah. Huh? Running average is easier.
I mean, it is complicated to have a system which is in the right way coupled to the environment in order to get this master equation.
Yeah, but you see, well, for this quantity, all that we did was the imaginary time that, the imaginary term that Jack was talking about.
In your numerics.
In our numerics, yes. Where you
No,
want
I
to do
think
it where? In the experiment.
I'm thinking about
But
an
in the experiment is good, right? People always have some kind of noise. So that's what we are telling them. If they get rid of T1 is the problem. No, if you're sucking particles, that's the problem. But if you have only dephasing, that's a good thing.
Okay, yeah, thanks.
Any other question? Well, I have one. Lea, is there any kind of optimal value for this dephasing strength so you can not lose information and still have smoothing?
We didn't do an analysis like to see how this bath is changed, and that could be done. We played with different values and small values. If you see there, was all 0.1, 0.0, 0.05, and the results were the same there. But checking how you're going to be destroying a hole, that's another thing to do.
Okay, thank you. Any other question? If not, let's thank Lea again, please. Los 30? Ah, sí, 35. 35, 30. 30%. Cuando faltan 10 y te veo, te enseño.
No, lengua todavía.
Ah, no, no. Ok.
Para que puedan papel.
Ajá. ¿Y ya lo pruebo?
Adelante, sí. Puntero. No deje presionados los botones porque sale la pantalla completa.
Perdón, ¿cuál es? Estos.
Ajá,
ah,
sí.
Ok.
Okay, now we have the talk of Mauricio Torres, who is my colleague in Puebla. And he will talk about Lindblad master equations without gain for strongly coupled hybrid systems. So please, Mauricio.
Thank you, Anthony, for the introduction. And I also would like to thank the organizers for the invitation and the opportunity to present this work. So this work was done in collaboration with these people. Artemisa Villalobos is doing her PhD at our institute. Ralph Betholz and Bruno Takitani, who was professor at Florianopolis, but now moved to the quantum computation industry. So the main messages of this talk are the following. So maybe this is, sorry, you are well aware about this, but there exactly solvable dissipative quantum systems do exist. So there are several, and I will tell you a little bit how this can be done and what do I refer to as exactly solvable. But the aim that I'm trying to do here is about the finding the eigensystem of the Liouville operator. So finding eigenstates, eigenvectors, and eigenvalues, right? So I will show that there are certain systems that do not possess any source of driving that can be triangularized and therefore can be solved exactly. You can find eigenvalues and everything. And then I would also like to mention that there are coupled systems that whose master equation is a little bit more complicated than is the ones that are taken in the literature. You have to derive them from first principles, and some of them can also be solved exactly. Because usually what people are doing is that if you have a system A, which is decaying, and a system B, which is decaying, what they simply do is that they take the system A plus B, so the open system, open equations for A and the open equation for B, and they simply plug in the Hamiltonian interaction between them. Well, this is good for weak coupling, but in general, this is not true, because as they are coupled, this coupling between them is going to induce a combined decay mechanism, and they are going to decay as a whole. And this is going, I'm going to refer to that as a dress-state master equation, and this is depicted by this. So A and B are coupled, you derive the master equation from the very beginning, and then you will see that they decay together, right? And this has certain benefits that I will show. In the weak coupling limit, this picture that is called also phenomenological master equation is fine. It doesn't matter. It's very good. But when the coupling becomes stronger, then you have to rely on the dress state master equation. And this is also important because nowadays in experiments, people are trying to go to that strong coupling limit, right? So even though deriving this type of equation might be a lot more complicated, I will also try to show you that the solution offers certain benefits. In some sense, it might be simple to obtain the full solution. So in order to do that, to achieve all those messages that I want to deliver or transmit to you, I organize my presentation in this way. First, I will give you an introduction, short introduction to Lindblad master equation. Then I will talk about the spectral decomposition. I mean, what do I mean by having eigenvalues and eigenvectors of this type of system? Then I will talk about triangular system, and then I will go through the strong coupling master equation and two examples, the James-Cummings model and an optomechanical system. Well, Lindblad equations have been already very successful in describing several systems of interest. For instance, atom-ion cooling has been, Lindblad master equations have been very successful in describing ion cooling. And also to get resonance fluorescence and describing systems like optomechanics and cavity QED. For instance, this is very nice because in trapped ions, they actually can infer the steady state of the motion of the atom, and also with resonance fluorescence you can infer get information about the motional state of the atoms, and everything all of this can be done in terms of within the formalism of Lindblad master equations. So what is the Lindblad master equation? Well, here I'm presenting one, the typical structure of the equation. So it's a dynamical equation for the density matrix, and you can think of it as a linear operator, the Liouville operator, acting on this density matrix that is written in this way. The first part here is just the von Neumann equation, and the part in red is called the dissipator. And this is the effect that you get from the environment, because the central system is going to be coupled to environment, and those effects are going to be described only as this red part. Another way of writing this equation that is going to become evident, that is useful in the following, is to separate this Liouville operator in two parts. One curly K operator and another curly A. This curly K is sort of a commutator, but not with the Hamiltonian, with this non-Hermitian Hamiltonian. Sorry, I missed an I here. There should be an I here. So this is the non-Hermitian Hamiltonian that some of you might be familiar with, that comes from the quantum jumps approach or the quantum trajectories. And this other operator, is called the jump operator. So in principle, many or some people have already been describing, I mean, it's possible to describe open quantum systems only using non-Hermitian effective Hamiltonians, right? And if you stay in that approach, you are able to describe everything within the state of vector formalism. However, the problem with that is that your norm is not preserved. If you take the trace of this guy, you will see that this is not zero, as it should be, because you are taking the derivative of a density matrix. This jump operator is what fixes everything. So in order to have that your norm is preserved, you require this jump operator. A simple way of visualizing this is take the following. This is an example of a damped harmonic oscillator. Here A and A Dagger are annihilation and creation operators. And here, this is the effective Hamiltonian, simply the Hamiltonian of the harmonic oscillator, and this part which is describing the decay of the system. So if you calculate the dynamics only using this effective Hamiltonian, you will see that the description is the following. You start with Fock state 3, for instance. This is the Wigner function for that state. And what you are going to see is that you are going to decay from this state, but you are simply losing the probability because you don't know where you are going to end up. So this part, this guy here only tells you that you are going to decay from level 3 or from level 2 or 1 or whatever, but there is no way to, you're not arriving to anything. So, but with this one, with the jump operator, this guy is ensuring that you go from state 3 to state 2, from state 2 to state 1, and in the end of the day, you get to the vacuum state. So, and this is also the Wigner function, where you see that here you go from the Fock state 3 to Fock state 0, to the vacuum state. And here, probability is simply lost. Well, now solvability of limb-lat master equations. Well, in the literature, you can find several solutions to this type of systems. And sometimes people refer to solving these systems as finding, for instance, a non-equilibrium steady state, right? Steady state solutions. This would be also a way of solving the solution to the system, but you don't find in those descriptions the full solution to the system, just the steady state solution, which is actually very good enough for several things because, for instance, in that case, you can find out the final temperature, the final occupation number of your system or whatever. But this is only restricted to steady states. There are also systems for which you can find systematic construction of solvable models, or you can also solve certain the time evolution of certain models for certain initial states and using some super operator techniques. But in general, all these suffer from the difficulties that you have a non-Hermitian nature of the generator. Your evolution is not non-Hermitian, and also the space is increased. If you have a dimension, the dimension of your Hamiltonian is n, then the dimension of the Liouville operator is going to be n squared by n squared, right? But in principle, this could also go to infinity, and even if you truncate that, it's going to be very, very large. So what I will show here is some solution for system with losses. I anticipate you that the steady state is going to be very boring. It's just, in general, there might be several steady states for certain systems, but most of the times, all those states are very boring. Something that has to do with a vacuum or something like that. However, it's good. I will show you that even in those cases, it is very convenient to find the exact solution for this type of system, and then you can use them. Well, spectral decomposition. So let's speak about certain operators. For instance, here I'm comparing the operators, the non-Hermitian Hamiltonian and the Liouville operator for the limb-lat master equation. In this part, the dynamical equation is given by the Schrödinger equation. Here, well, this is the limb-lat master equation, and you have in the left part you have an eigenvalue equation, which is a dual master eigenvalue equation, because as your operator is non-Hermitian, you have right and left eigenvectors. Your eigenvalues epsilon are going to be complex numbers. Then you have also this orthogonality condition between the left and right eigenvectors. And you can also evaluate the time evolution of the system given an initial state in this way. Notice that if K happens to be an Hermitian operator, then this is the usual way of that you learn in quantum mechanics, because this is simply the initial probabilities amplitudes, and this in the basis of the eigenstates, and these are the eigenstates. Something similar you can do with the limb-lat master equation, and there you have also a dual eigenvalue equation. So you have L, rho. These are going to be my left eigenvectors, and lambda is going to be the the eigenvalue. Here, I don't know why a dagger is missing. So you can apply L dagger to the left ones, well, the adjoint ones, because in general this could be an infinite system or so. And then this is going to give you the lambda star, this other guy. You also have an orthogonality condition with respect to the Hilbert-Schmidt inner product that you can write in this way. And using that, this is the analog part of this. You can also evaluate the time-dependent state for any initial condition, rho 0. Okay. Well, the simplest example that I can show you about this type of eigensystem is for the two-level system. Think of an excited state, a two-level atom, an excited state, an energy different h bar omega, and a decay rate gamma. The Lindblad master equation is given in this form. And you can find that the eigensystem is given by this. These are the eigenvalues. And these are the right eigenvectors and the left eigenvectors, right? Which are written in terms of Pauli matrices. You can check that this is actually solve this the eigenvalue equation for this superoperator. And another way of finding it is actually by vectorizing your density matrix. So you take your density matrix, which is going to be 2 by 2 because you have a two-level system, and you put it as a vector of 4 dimension. And then the Liouville operator is going to look as a 4 times 4 matrix. And one thing that you can notice here is that this operator is triangular. So the eigenvalues are actually the elements in the diagonal. And these elements in the diagonal, of course, coincide with these eigenvalues that I have written here. Another solvable model that is known is the damped harmonic oscillator, which is can be in contact with a reservoir at finite temperature, not only 0 temperature. And so this is the master equation. So you have two terms. This term is the one which is cooling the system, and this one is the one that is heating the system. These are one of the few models where you can find non-trivial steady state. The eigenvalues are easily found to be, well, not easy, but it can be found in this way. Actually, what you have to do is you can turn this into a differential equation. You find Komar's differential equation, and you find that these are going to be the eigenvalues. And if you do that, you find that the right eigenvectors and right and left eigenvectors are given in terms of Laguerre polynomials of normally ordered bosonic operators. The steady state, of course, is given here, and it's actually a Gibbs state. It's given here. Well, what can you do with this? So imagine that you already have solved the system. You have the set of eigenvectors and eigenvalues. What you can do is you can apply it, for instance, to a problem of resonance fluorescence. The resonance fluorescence of a driven system, for instance, so you drive the system with a laser here, and in response, it is going to emit light. And you ask yourself, at which frequency is this system emitting light? Well, this is going to be related to a correlation function of operators evaluated at different times that you can write in this way. And if you know the spectral decomposition of L, then you can also expand this in this way. So actually, resonance fluorescence spectrum with this form here, you can notice that are going to be given by Lorentzian functions and Fano-shaped profiles. And this is it. And these are going to be centered in the real part of the eigenvalues, sorry, in the imaginary part of the eigenvalues, and the real part is going to give you the width of these Lorentzian functions. An example that we did some time ago is for this type of quantum emitters. imagine that you have a lattice of atoms and a defect at some point. If the and this in this defect is if there is a spin or an electronic state, that if it's in the excited state, is going to push away the other atoms in the lattice. So what you do here, you have this the physics can be described in this way. This is the Hamiltonian. So you have the B here is going to be a normal mode of all the lattices of the atoms oscillating. These are the electronic levels of the emitter of the or the defect, and this is how the defect is pushing the other atoms, right? If it's in the excited state, it's going to push away all the atoms. If notice that if the electronic state is in the ground state, then this term vanishes. Here, what you have is that you can you get decay for the electronic part, but you have also damping in the oscillations. The damping in the oscillation are going to be given in this part. The damping in the electronic states, you can think about you can consider them as interacting with a zero temperature bath, because for optical frequencies, there are, if you turn off the light, there are no photons, right? So you can think that you are in the vacuum state. But this is not true for the vibrations. In the vibrations, you have to take into account the temperature, and this is encoded by this m bar parameter. And if you look at the spectrum, it's going to look something like this. And this is a typical form of the spectrum that you see, for instance, when you look at the emission spectrum of an NV center, for instance, it looks something like this. And here we can decompose this type of spectrum in terms of Lorentzians and Fano profiles centered at the imaginary part of the eigenvalues and with the width of the real part of the eigenvalues of the system. So this is an application that you can have, even though we are deriving the eigenvalue or the eigensystem for a system which has a very trivial steady state. You can already do several interesting stuff with it. Oh, sorry, can you fix that? Thank you. Well, now let's go for triangular system, how you can solve them. I go again in this way of writing the Limnad-Master equation in terms of these two super operators. And I'm going to assume the following. I'm going to assume that I have a solvable Hamiltonian. This could be something like, I don't know, interacting atoms, the James-Comics model, something that has to do with angular momenta, where you have certain degeneracies or so, where you can define a constant of motion I that commutes with the Hamiltonian. And this constant of motion might have a degeneracy dn. So for each number n, there are dn states that have the same eigenvalue for I. And also, I'm going to assume that this A commutes with these Limnad operators, or have this commutation relation with the Limnad operators. This is also the typical commutation relation that you have, for instance, of the number operator with the annihilation operator. And of course, this constant of motion has to commute with the Limnad operators written in this form. If you do that, it follows that because I commute with H and I commute with A dagger A, each of the A dagger AS, it will also commute with K, which is this effective Hamiltonian. So this means that if H is block diagonal because of this degeneracy of the constant of motion, then K is going to be also block diagonal. You can also think of other commutation relations. For instance, it could be 2AS or any other integer number. This is also possible, but I will restrict myself to this case. Because one of the typical systems that fulfills these conditions is the James-Comics model. The James-Comics model has this constant of motion that commutes with H, has the same commutation relation with the Lindblad operators, and therefore you can block diagonalize the non-Hermitian Hamiltonian in this way. So once that you have this non-Hermitian Hamiltonian, you can evaluate its left and right eigenvectors, also with the eigenenergies. And once you do that, you can you realize that if you have already the eigenstates right and left eigenstates of K, with that you can also diagonalize curly K, the curly K superoperator, because it's going to be only the Ketra elements formed by the eigenvectors of this system. And in this way you find already the right and left eigenvectors of curly K. And the eigenvalues are simply going to be given by the sum of the eigenvalues of the non-Hermitian Hamiltonian. And you can show also that these elements here are orthogonal with respect to the Hilbert-Schmidt inner product. Now, but we don't want only oh, sorry again, can you fix that? We don't only need the eigensystem of curly K. We need the eigensystem of the complete Liouville operator. So what do? Well, then we have to know how the jump operator is going to act on these elements. And you can realize that actually you can represent this Liouville operator in terms of direct sum of several subspaces. And this is the density matrix, and what you will see is that the Liouville operator is going to be also block diagonal, well, with also another diagonal above the main diagonal that is coupling these blocks. These actually are blocks of the curly K operator. And this jump operator is only coupling this guy with this guy, and then this guy with this guy, and so on. And because this is a triangular system, the only thing that you have to do is diagonalize the diagonal part. This is of course going to change what is in the upper diagonal, but you will see that the eigenvalues are going to be, well, the elements of that diagonal. So the eigenvalues of curly K and of the Lindblad operators coincide. What are we doing here at the level of the density matrix? Well, this part, this L is actually how elements of the density matrix in diagonals are coupled. You have an L0. L0 is how the elements in the diagonal of the density matrix are coupled. And so finding the eigenvalues is the easy part. Finding the complete set of eigenvectors of L, it's a little bit more complicated, but it can be done, because what you will end up with is that you get a recurrence relation for the coefficients. You make the ansatz of the complete set of eigenvectors in this form. So you put it as a sum of the eigenvectors of curly K, and then you will end up with a recurrence relation for the coefficients that can be solved. It can be solved because it's a vectorial recurrence relation, but it's of first order, and this type of recurrence relations can be easily solved. Well, now let me tell you about the strong coupling limit. What's changing here? Because here I was telling you in general about how to get this type of solutions, but now I will tell you a little bit of how what happens with strongly coupled systems. Well, let me first show you a sketch of the derivation of the Lindblad master equation. We start with a closed system where you have the Hamiltonian of the total system, the Hamiltonian H of the central system, the Hamiltonian HE of the environment, and the interaction between them. Of course, this can be described by the Schrödinger equation of if you have a density matrix by the von Neumann equation. Now think about that you take partial trace of this von Neumann equation. This part here is going to cancel because you are taking the trace over the environment, and here is this a commutator with operators from the environment, so this is going to be left out. This is going to be only the commutator of H with the reduced density matrix of the system for the system, and this part here, the trace for the interacting part, is where the Lindblad dissipator comes from, roughly speaking. There are still some things to care about, but essentially this is more or less the procedure. This looks a little bit complicated, but what you essentially do is that you have the von Neumann equation, you integrate it formally, and then you put it again into this equation. So this is why you get a second commutator. You take the partial trace. All this is done in the interaction picture. But a key observation here is that what you require here is to know the interaction part. You separate the interacting part with V times BE, and you require the interaction part of the Hamiltonian in the interaction picture. You have to know that. If you don't know that, it's not going to be possible to derive the dissipator part. So what you do, this is what this can be done. We found in the book of Petruccioni. You introduce these projectors onto the eigenstates of the central system, and then you split this B, which is the interacting part for the central system, in all these L's that I have here. Because these are projectors on eigenstates of the central system, in this way you can find actually what the form, how the interacting part behaves in the interaction picture. So because here you can actually, when you apply e to the minus IHT to these guys, you only get the eigenvalues. And this is why you get this equation here. You plug this in here, you make the integration, and you perform what is called the rotating wave approximation, and you end up with this type of Lindblad master equation. But the key observation here is that you require the eigensystem of the central system. You need the dress states of the central system. And this is how you get a Lindblad master equation, or the dress state Lindblad master equation. So it is not true that if you combine simply the system A and B and you plug in the interacting part in Hamiltonian form, that you are going to be describing faithfully the system, because this is not the way that the system decay. For that, you have to, they actually decay following the dress states of the central system. So in the weak coupling limit, it is fine to do that, but if you have strong coupling, then it is not longer true. So a simple example, or the simplest example that we can think of, is two interacting two-level systems. So this is the energy part of the first two-level system. This is the second one, and they are interaction with this dipole-dipole coupling, if you wish. This is going to have a matrix representation of times 4 times 4, so you can evaluate eigenvalues and eigenvectors in a simple way, and we assume that they are coupled to a bosonic environment. When you derive the dress state Lindblad master equation, you will see that the Lindblad operators are going to be transition between dress states. And for certain conditions, this does not always happen, but you can get actually that you go from the excited state, both atoms in the excited state, to one of the rest states, and then from here directly to the bottom one. So the minus state here, which is written here, this one here, is decoupled from the damping dynamics. So it's actually a decoherence-free state. And this decoherence-free state is not present if you look at the phenomenological master equation, where you see that the Lindblad operators are simply the connection between the bare levels of the two atoms. In this description, you go from the two atoms in the excited state to one in the excited state and the other in the ground state. And you can also go de-excite the first one or the other one, and then here you can go to the bottom one. So interesting features appear already when you start describing things properly, let's say. So in this is the first one that you can have a decoherence-free state. But also another one which might be not quite evident here, but if you see these 1 and plus, ket 1 and ket plus, are the eigenstates of H. So this means that you can also put this state here can be also diagonalized in terms of those states. So ket 1 and ket plus are also eigenstates of K. And this is quite interesting because now this means that this operator here can already be diagonal in the rest states of the Hamiltonian. So it is actually a normal operator. In this case, it is not. In this case, in the phenomenological equation, you have to find right and left eigenvectors. Here, right and left eigenvectors coincide because they are the rest states of the central system. Okay. So in some sense, you spend more time deriving the correct Lindblad master equation, but the solution itself is going to be more simple because the structure of the operators is much simpler. You don't have the non-Hermitian Hamiltonian is going to be a normal operator, so you can diagonalize it with a unitary transformation. And actually, you have already the transformation because it's given by the rest states. Well, now the James-Cummings in the strong coupling regime, you can also find it. This was already done by these people here, Maniscalco and other people. And now the Lindblad operators are not difficult to obtain. They connect also the rest states of the James-Cummings model and are given in this way. Unfortunately, here you cannot put it in as you had before, like you get that one of the Lindblad operators is the annihilation operator or the decay operator of the atom, but you have to put it only in terms of transition between rest states. This looks a little bit nasty, but when you look into the solution of the system, there are two things that you can find. First of all, again, the Hamiltonian is going to be a normal operator. And because of this structure that you have, you only are going to couple elements these are meant to be blocks of the density matrix. So this is going to be a 2 times 2 block, 2 times 2 block, and so forth. But what is happening here, because you have this structure between only connecting rest states, only in the middle part, you will get a recurrence relation. All other of diagonal blocks are going to decay by themselves. So they are not going to be coupled to any other block. And this, of course, makes also the solution much more simpler to evaluate. So any of diagonal element in different blocks are going to be evolving in time in this way. Okay. So this is what I was telling you, that you have here a normal operator that is written in terms of the eigenstate of the James-Cummings model, and the eigenvalues can also be evaluated simply. And because this type of system also fulfill the conditions that I showed you at the beginning, well, you can also find the eigenvalues. How much time do I have? Okay. Well, I think I will leave it here just to, very rapidly. Something similar you can do with optomechanical system. And here, the only observation that you have to do is that you will have another operator which is equivalent to K. And you can also find the complete set of eigenvalues and eigenvector, and in the details I have here if anybody is interested. But okay, from that you can also evaluate the absorption spectrum of the cavity, for instance. And here I'm showing you only the difference between one of the description, the phenomenological, and the Dresde master equation. Well, to summarize, well, what I have shown you that Limblad master equation can be triangularized. Everything can be evaluated, eigenstates and eigenvalues. For certain strongly coupled system, this also applies. And the important thing is that here you have combined decay mechanism that can make things interesting, such as having decoherence free states and stuff like that. And well, non-Hermitian operator, the non-Hermitian Hamiltonian is a normal operator, and it also simplifies very much the calculation. Well, thank you for your attention.
Thank you very much, Mauricio. Is there any question here? Please.
Yes, I have a few questions. For example, when treating these open systems in terms of these eigenvalues and eigenvectors of the Limblad, this somehow fix you the initial conditions of the system, because you can work with you have to fix where are your initial conditions. You cannot simply start with anything, but perhaps one would like to start with arbitrary initial conditions and then transit to this eigenstate solution of the whole Limblad, which will be imposed through the dynamics. Somehow maybe one loses some of the transients of this thing, or not? Do you know?
No, not really. Actually, that's not the case. You can start with any initial conditions because you have the complete set of eigenvalues and eigenvector. Just as when you get diagonalized your Hamiltonian,
yes,
you are not restricted to the initial state.
But also, for example, not pure states. For example, suppose you start with something which is...
You can start with whatever you want. With any initial state can be pure, can be mixed, whatever you want. Well, the only thing that you are restricting yourself is with the constants of the model, if you wish, but not the states.
Mm-hmm. Okay, now this was also a question, and in the case of this Dresde state solution, I think it's also called global master equation, these approximations, or this is not the case.
Which one?
Global master equation, the treatment you did for the Dresde state solution for the two-party system coupled to...
I think that is another one. This is the Dresde state master equation.
Okay, this is a different thing.
Yes.
So in this case, for example, one thing that one used to do to get Limblad form when doing microscopic derivations is this secular approximation, which somehow you get rid out from transitions of further levels and just keep neighboring levels. Yep. But in the Dresde state solution, you still do this kind of approachment.
Yeah, and actually this approximation is what is making you, it's what is giving you this behavior here. Precisely. That you are not coupling these blocks, but only these ones here.
But wouldn't that somehow omit part of what you would like to see also? Because you would like to not only see probably transitions between a region of eigen energies of one subsystem and the other one, but also transitions in between the same system?
You are seeing transition between the systems. The only thing that you are not seeing here is the transition between the off-diagonal parts. This is the
Both diagonal parts also connect the spectrum from one system to the other, right? Because they are interacting between them. So they're somehow entangled. They get entangled. I mean, you have two systems here, A and B.
Mm-hmm.
So you have this rest state, which is an entangled state of A and B. But you see transitions from
So
A.
maybe to be on the schedule, so we can postpone the discussion for the coffee break.
Sure.
Thank you. So let's thank Mauricio again. Mark, when you have still 10 minutes left, and then
Okay,
5.
that's good. Yeah, okay.
This is to go the next slide, go back, pointer, and if you press a large time in the bottom.
Too long, then it will, okay.
Go out.
Okay.
Which one?
So it works? Yes.
Okay, now we have Barbara Dietz from South Korea, who will talk about the Rosenweis-Port model revisited from the 3 Wigner-Dyson ensembles. So please, Barbara, come on.
Yeah. First, I would like to thank the organizers for inviting me and for giving me the opportunity to talk here about some work which I did together with, no, I didn't want that. This one. So which I did together, they all were at IBS. So Tillen and Alexei are still there, but Dario, he went to Sao Paulo, and Dilip, he went back to India. And this is some work we did together. It's about the Rosenzweig-Porter model, which actually was introduced in the 1960s in context of nuclear physics and describing spectral properties of the energy values. And then it was came up again in the context of quantum chaos to describe spectral properties, and recently also in many-body quantum chaos because it can be used to describe properties of the eigenstates. So and I will talk about, and we extended that work to the symplectic universality class, and it will be published soon in a new journal of physics, but you can also find all what I will talk about on archive. So just to briefly remind you that quantum chaos, it refers to the study of signatures of classical chaos and properties of quantum systems, and the one central aspect are properties of the eigenvalues. And so there are 2 central conjectures. One is by Berry and Tabor, which states that the spectral properties of systems with an integrable classical limit behave like random numbers from a Poissonian process. I don't need to go into details. And the other one is the Bohegas-Giannoni-Schmidt conjecture, where it's stated that the spectral properties of typical quantum systems with chaotic dynamics in the classical limit are coincide with or agree well with those of random matrices from the so-called Gaussian ensembles. I will restrict to the threefold way, Dyson's threefold way, so to ensembles with orthogonal, unitary, or symplectic symmetry, universality class. Just to remind briefly, I mean, the random matrices from these Wigner-Dyson ensembles are random matrices which are Hermitian and have Gaussian distributed matrix elements. And if you have a system with an integer spin and preserved time reversal invariance, these are described by those random matrices that are real and symmetric, and the time reversal operator in this case is given by a complex conjugation. If you don't have time reversal invariance, then the random matrices are Hermitian and belong to the unitary universality class. So these are orthogonal unitary class with beta equal to 1, and this is a unitary universality class with beta equal to 2. And if you have a quantum system with spin 1/2 and preserved time reversal invariance, then the time reversal operator is given by complex conjugation multiplied with y, and this y is a symplectic unit matrix. So here 1 is a unit matrix, and zeros are zero matrices. And the Hamiltonian is then symplectic in that case. And also quaternion real. And in this case, I mean, t square is equal to -1, and then the eigenstate and its time reversal are orthogonal to each other. Therefore, in that case, you have Cramer's degeneracy. So just to repeat some of the spectral properties which are considered in context of quantum chaos are the most famous one is the nearest neighbor spacing distribution. You can derive very good approximations starting from 2 by 2 random matrices, and these are the Wigner surmises. So they are described by a Gaussian decay, and for orthogonal, they are proportional to the spacing for small spacings, for unitary proportional to s squared, so symplectic s to the power of beta in general. And these are very good approximations which are generally used to compare to spectral properties of a system. There's another distribution. These are the distribution of consecutive level spacings, ratio distribution. And in this, these are essentially, this is a distribution which is used now because the ratios are dimensionless. So in that case, you don't need any unfolding. Whereas to get the nearest neighbor spacing distribution, you have to unfold the eigenvalues to some uniform spectral density. And this is not required when you use ratio distributions. And these also can be derived, I mean, good approximations by starting from 3 by 3 random matrices. And for Poissonian, you can also derive general expressions. So I just want to show how simple the expressions are in that case. Also, for the 2-point cluster function, they are known analytically. And starting from this 2-point cluster function, you can, first of all, for Poisson, it's simply equal to 0 for n larger equal to 2. And like the number variance, which gives the variance of the number of eigenvalues in an interval of length L, where the eigenvalues are unfolded. It can be obtained by starting from the 2-point cluster function, also the spectral form factor, which is a Fourier transform of this 2-point cluster function. It can also be obtained from this analytic expression. So for the Wigner-Dyson ensembles, you have analytic results for all 3 universality classes. Now, in the first application of random matrix theory was in nuclear physics. This is a famous nuclear data ensemble, which was taken from 1,726 resonance energies, which were taken from 30 atoms and from 27 different atoms and 30 sequences of eigenvalues. And for that case, it coincides very well with Gaussian orthogonal ensemble. So this is a Wigner surmise for GOE. Also the rigidity, which is a measure for the rigidity of a spectrum, agreed very well with Wigner-Dyson for the GOE case. Now, generally, the spectral properties of the nuclei are similar to those of chaotic systems, quantum chaotic systems, or typical classically regular systems. However, in that case, you don't have an obvious classical limit. It does not exist. So in that context, one speaks about of collectivity of the many bodies like nucleons in the nucleus. Then you refer, so Poissonian is identified with collectivity and complexity of the motion of the nuclei, for example, with Wigner-Dyson behavior in general. Or you can, what is done currently, what you would call quantum chaotic or many-body quantum chaotic, that you study the properties of the eigenstates. So you would find many-body localization if you have a collectivity of the motion, and ergodicity if you have a complex motion. So, and I will speak about all that now in the following. For the Rosenzweig-Porter, so the first realization, which was proposed in the 60s by Rosenzweig and Porter and then used in quantum chaos. It can be written in this form. I mean, the spectral properties are intermediate between Poisson and Wigner-Dyson statistics, so they are used, for example, to describe the spectral properties of systems with a mixed regular chaotic dynamics. And it's given as a sum of two terms. One is H0, it's a random matrix, diagonal random matrix, and the elements are arbitrarily distributed. And this H beta is a random matrix from the Wigner-Dyson ensemble with index beta. And this term here, lambda, it controls the deviations from integrability, and this parameter gamma, it has to be introduced. I mean, both the eigenvalues and this parameter lambda needs to be rescaled to ensure universality of the properties of the Hamiltonian system. I didn't want to go further, so yeah. Wanted to stay here. So this, the eigenvalues are unfolded by replacing them by the smooth part of the integrated spectral density. And the parameter gamma, it gives the scale of this parameter for one possibility. So there are several possibilities. One is to choose the eigenvalues of H0 and H beta such that they take values between -1 and +1, and to use for gamma n the average of the spectral density, so the semicircle law. You would take here the semicircle law. And the other one would be to replace gamma, to use for gamma n the variance of the diagonal elements of H beta divided by the length of the eigenvalue spectrum of H0. So there are different properties. So, and in this ensemble, so there already in the 90s, there have been derived Wigner surmise-like expressions for the nearest neighbor spacing distributions, again starting from 2x2 matrices, so they look much more complicated than for the Wigner-Dyson ensembles, but they are very useful to get information on the parameter lambda or on the degree of chaoticity of a quantum system. Another one we derived in this is given in this NJP, Wigner surmise-like expression for the R ratios of for the transition Poisson to GUE. And it's again starting point are 3x3 matrices, and only for that case, for the transition to beta equal to 2, when the joint probability density of the eigenvalues is known. And so this can be used to get an analytic expression for GOE, which looks very complicated, but it describes data so it's a very good approximation. And also for the cluster functions, you have analytic results for the case GUE, again starting from this joint probability of the eigenvalues. And it looks much more complicated than for the Wigner-Dyson ensembles, but the agreement is very good again with random matrices from Rosenzweig-Porter. So and recently, a few years ago, Wigner-Rosenzweig-Porter came up again because people realized, so in Kraftstorff et al., they proposed a reparametrization, so they replaced lambda by 1 over n to the power of gamma over 2, where n is the dimension of the random matrices and gamma is now the parameter. And if you do this, then one can identify 3 different phases as concerning the properties of the eigenfunctions. They're first of all for gamma equal to 0. I mean, the variances of the random matrices are chosen such that for gamma equal to 0, you just have a random matrix from the corresponding Wigner-Dyson ensemble. For gamma equal to 1, a phase transition takes place from ergodic extended eigenfunctions to multifractal. So, and that in between for to fractal dimensions, so in between between gamma equal to 1 and 2, you have a fractal eigenfunctions. This is the third phase, which was detected by this rescaling. And for gamma equal to 2, a transition to localization takes place. So that was, for that reason, Rosenzweig-Porter came up again. And this, it's called the generalized Rosenzweig-Porter model. And here we studied nearest neighbors, so spectral properties for the Gaussian symplectic ensemble, for Gaussian orthogonal and unitary. They were known, and I mean, here I just plot for different values of gamma, the nearest neighbor spacing distribution, integrated nearest neighbor spacing distribution, and to study the transition from Poisson to the Wigner-Dyson ensemble, we looked at the position of the maximum. And as one can see here, up to about gamma equal to 1.5, you don't see any changes. So up to that case, I mean, it would be expected that changes are expected above gamma equal to 1, but for the short range correlations, you see them only above gamma equal to 1.5. So these are the positions of the maximum, like here for the 3 different Wigner-Dyson ensembles. So the same for, here I show it again. So to obtain information on the chaoticity of a quantum system, you can use these Wigner-Surmise-like expressions, and that here we use them to get lambda as function of gamma. So the agreement is very good, and by fitting these expressions to the random matrix simulations, you get the lambda as function of gamma, and as expected, it's proportional to 1 over n to the gamma over 2. But if you now have a quantum system and want to know something about the spectral properties, you can use these Wigner-Surmise-like expressions as long as you are above gamma equal to 5. Below, you don't get much information. And here I show R ratio. So here, this is a turquoise curve is a analytic result, and the average R ratios are considered to get information on the evolution with the parameter lambda or gamma. And here again, one doesn't see much changes up to gamma even equal to 1.6. That is, below they don't feel anything of the transition from ergodic extended to fractal, so non-ergodic phase. So what one usually looks at is not the average of the ratio distribution, but the average of the Rj min, which is obtained by taking either the Rj or 1 over Rj as quantity, and this depends on which one is the smaller one. And here I show it in a 3D plot. I mean, here we computed R min as function of gamma and as function of energy, and one can see that the transition takes place. It depends on both energy and on gamma. So that you have here you have the transition to ergodicity. It's along this line. Now so that's in energy resolved space, and if you now average for a fixed gamma over the whole spectrum, then you get these 3 curves for the minimum. And here you can see that the changes are observed only above gamma equal to 1.6. So short range correlations are not a good measure to get information on the degree of chaoticity as long as you are below gamma equal to 1.6. But you can use them to identify the Anderson transition from ergodic to localized, because if you here I plotted the ratio distributions for different n, and they all cross in one point, and this is exactly gamma equal to 2 where the transition takes place. That is, at this point, the distributions don't depend on gamma. So we also looked at long-range correlations. So this is not so here. This is just to compare analytic with RMT results. And here I show now the number variance for the GSE. For gamma equal to 0.9, it's on top of the GOE curve. And with increasing gamma, it immediately above gamma equal to 1, you see deviations in this case. So there you have them exactly at gamma equal to 1. You see the differences, and to study these, to quantify these deviations, we looked at the distance of the number variance from the Poissonian curve. So these are these curves here in this paper, and from Wigner-Dyson ensemble. These are these curves here. And the distance is non-zero for gamma equal to 1, and for gamma above 2, so like at gamma equal to 2.2, so we have agreement with Poissonian distribution. Another measure is compressibility. It's defined as the asymptotic behavior of the number variance for very large values of L. You can use this quantity if it then increases linearly with L. I mean, for the Wigner-Dyson ensembles, it behaves logarithmically, so for that case, you would have gamma equal to 0, whereas above you can compute this compressibility, and then we get these curves. And here again you see changes above gamma equal to 1, and then above gamma equal to about 2 they saturate and don't change anymore, because then you are in the localized phase. The same for the spectral form factor. Here I just show the results for GSE. For GSE, you have a logarithmic singularity at t equal to 1. And below the minimum would be at 0 for Wigner-Dyson. And we now looked at the change of the position of the minimum and the size of the minimum as function of gamma. And this is plotted here. And then you can see that above gamma equal to 1, you see changes from, so it's non-zero, and it increases, and at some point it reaches a value. I mean, you don't have a minimum. At some point, minimum, it moves more and more to the right, and for here, we don't have it anymore. For gamma equal to 2.5, you don't see any minimum in the range up to t equal to 5. So this can be used to study the transition from ergodic to localized. Another quantity is a power spectrum, which has this property. So the power spectrum, you take the Q's distance of the eigenvalues, the average minus Q, and then you compute the Fourier transform, then you get the so-called power spectrum. It has a property that for very small values of Tor, it should have an algebraic behavior. And for all three Wigner-Dyson ensembles, this power is equal to 1, whereas for Poisson it's equal to 2. So it can be used to distinguish between integrability and Wigner-Dyson properties. And here I plot the minimum as function. So this parameter mu this as function of gamma. So one can already see here in this plot where I show the power spectrum for the GSE that I mean at below gamma equal to 1 it's very close to the asymptotic behavior, and also for Poissonian, you see good linear increase, so like t to the minus 2 in this case, and here it goes like t to the minus 1, and in between you see increase in the power of mu, and this is seen here as a maximum. So around gamma equal to 1.4 to 1.3, you have a maximum, and then it saturates, it goes back and saturates at the value for Poisson. So generally, so here just show one example for an experiment which was done during my time in Lanzhou. So there we wanted to study so Rosenzweig-Porter experimentally, and for this we use a cavity microwave billiard, which is circular, and at the center it has another disk, so it would be microwave billiards can then be used to simulate. This one can be used to simulate or to get experimentally the eigenvalues of a quantum ring billiard, because the Helmholtz equation coincides with the Schrödinger equation of a quantum billiard in a certain frequency range. So we replace the disk at the center by a ferrite magnetized from the outside, and then you get a transition from Poisson to GUE. Or if you add a small disk, then you can see something in between regular and GOE behavior. So here I just show examples for the case where you have just a ring billiard with no magnetic field and no additional scatterers, then it should be Poisson. And the green curve here shows the quantum billiard, the red one the experimental result, and they are indeed close to one another. And we had only 1000 resonance frequencies, and then you don't have agreement with Poisson, but with something which is close to gamma equal to 2.1 if you now fit the Rosenzweig-Porter to the curves. And when you here, I show results for the case where in this case, we added magnetic field so we magnetize, and then you see a transition to from Poisson to GUE, and gamma in this case is equal to 1.8. And here one example where we added two scatterers. There you have something between integrable and GOE behavior. So this is just one example, experimental example. So now to summarize spectral properties for the short-range correlations, you see a transition, the ergodic transition only above gamma equal to 1.4 to 1.5. You can use a ratio distribution to identify the Anderson transition at gamma A equal to 2. Long-range correlations immediately see the deviations from Wigner-Dyson behavior above gamma equal to 1. And however, in order to unambiguously identify the ergodic or non-ergodic and Anderson localized phases, one needs to look at properties of the wave function. That's what I'm going to do now. I mean, there are already eigenvector distributions have been derived by Bogomolny and Ziba and studied extensively, and we now looked at different measures for the properties of the eigenvectors. Here I show results for the participation number as one example. Here psi mu is the eigenstate corresponding to the eigenvalue E mu, and I is a component of the eigenvector. So these are participation numbers. They are shown here. So they are should be close to 0 in Wigner-Dyson, and then go up to some non-zero value when you come to Poissonian distribution. Another example, quantity we looked at is our fractal dimensions. They should be equal to 1 for all Q values as long as you are below gamma equal to 1, and then above gamma equal to 2, they should be equal to 0. So that would be Poissonian behavior. And in between, the prediction was that they change like 2 minus gamma. So the fractal dimension and the fractal phase is 2 minus gamma. And another quantity is a participation entropy. So these are typical measures that are studied in the context of many body systems, and they can be described by the Rosenzweig-Porter. And I should mention that in the case of the so for the symplectic ensemble, you have these gamma degenerate eigenvalues. So for the spectral properties, of course, you have only n/2 eigenvalues available. And here one has, in this case, we could use all eigenvectors. However, when you come to the Kullback-Leibler divergence, there one can use only one of the eigenvectors, either for the analysis. I mean, we looked at Kullback-Leibler, this kappa, it's called K2 in this case, so we call it Ke because it measures ratios of eigenstates mu and eigenstates of another realization where we chose the mu prime such that the corresponding eigenvalue is closest to the eigenvalue E mu. So in this one, it measures, is an indicator for the ergodic transition, therefore we call it Ke. And we also looked at this quantity. I mean, it measures ratios of an eigenstate and of the neighboring eigenstate. So it gives information on the Anderson localization, the Anderson transition. And here in this case, you use only one of the two eigenvectors corresponding to degenerate eigenvalues. And in this case, we used either of them. And both can be used to identify the ergodic transition. You can use this Ke because there, when you plot several results for several dimensions, then they all cross at gamma equal to 1. And for this quantity here, they cross all at gamma equal to 2. So they can be used to identify the ergodic and Anderson transition. And another quantity is finite scaling. It's another quantity that is studied, and so there the behavior in the vicinity of the crossing point can be derived by this quantity, where this nu is equal to 1 for Anderson and ergodic transition, and it's the same value for all 3 universality classes. Therefore, we would call it super universality. So here I just show the results for symplectic ensemble, but you would get similar results for the orthogonal and unitary ensembles. And another quantity which both is sensitive to the properties of the eigenvalues and also of the eigenvectors is adiabatic gauge potential, which is directly related to the fidelity susceptibility. I mean, to obtain it, we have to perturb, so the Hamiltonian, in our case, the generalized Rosenzweig-Porter Hamiltonian is perturbed by some parameter-dependent potential here. This matrix V, it's a constant matrix which consists of random, it's a diagonal matrix with box distributed elements, and epsilon is a parameter. Now the adiabatic deformation is defined via this adiabatic gauge potential, which is just given if you apply it to an eigenstate, which these are all epsilon dependent, then it's given by I times d by the epsilon of L of I epsilon. Now, if you take the limit epsilon to 0, then you can, the matrix elements of the corresponding states, between corresponding states, is given by this term here. And in our cases, d by d epsilon is very simple because this is just matrix V, and that's the reason why we chose it like that. And fidelity, susceptibility, or it's also called adiabatic gauge potential, is then obtained by taking the by taking the absolute value square, and then it's given in this form. And as you can see, it depends both on the eigenvalues and on the eigenvector components. And of course, one has to sum over m not equal to L, and for the symplectic ensemble, one can only sum over one pair of eigenvalues. So for example, those with an odd index. So that's again, some of this fidelity susceptibility can be used to identify both phase transitions. Namely, when you plot it for different dimensions, then all curves cross at gamma equal to 1. So this gives you the ergodic transition, and they all exhibit a maximum at gamma equal to 2. And this means that the derivative at that value has a crossing point. So you can use it to identify both transitions with one statistical measure. So, and summarizing the results, for all 3 Wigner-Dyson ensembles, one has the same value for the ergodic and Anderson transition, and also these finite size scaling yields the same result for the power. It's equal to 1 simply. So for all, all these eigenvector measures can be used to get information on ergodic or Anderson transition. So, and you get the same, therefore we call it super universality. So on this I would like to thank you for your attention.
Okay, thank you very much, Barbara. So is there any question? Please.
I'm a bit interested in the special case you used with where you have scatterers. Is it clear that a small classical perturbation of a integrable system is best modeled by the Porter-Rosenzweig model? The eigenfunctions just look very strange for such a system.
Yeah. I mean, if you chose them too small, then you would have singular statistics. I mean, we also did experiments where we simply use long antennas, and then you get a so-called singular billiard, and then you don't have agreement with Rosenzweig-Porter. So you have to make sure that the perturbation is large enough to simulate the transition from Poisson to GOE. Yeah. So we compared with both statistics, and then and for that case it was better with this Rosenzweig-Porter.
Okay, is there any other question? Yeah.
And if, in that case, if you compare to Berry-Robnik with a superposition,
yeah,
or to the Brody conjecture, does it work better or not?
I mean, I only I mean that for the singular billiards, I compared with for these experiments with singular billiards, which we did in Darmstadt. I also compared to Berry-Robnik. And there I found better agreement with the results. By Bogomolny, he derived results for singular billiards, where you have a delta potential perturbation. And there it was clear that that description was better.
Okay, any other question? Well, then let's thank Barbara again. So with this, we end with the morning session of this of today's conference.
But it's certainly that's something which is at least I would say new. That's good to do.
Yes.
Yes.
I don't know whether you know our other colleague is called Shadow Waller.
Yeah, sure.
And he's half retired, but also active. And he's also.
Yeah. I mean, I think it might not be so easy actually. Personal time because you can go to some of these groups to meet them.
Yeah.
Yes. But then also arguing all the information that says about that they don't see but
Yes. I already encouraged him to have contact with Steve Barnett in Glasgow.
Mm-hmm.
He contacted Steve, hesitant to visit them because he doesn't like the feeling sitting at the others.
But
it's an encouraging experience.
of course, the way we go to conclusions that are experimental.
Yes.
We do is these connection stuff to actually theory.
Yes.
Just being about
Yes. Yeah, but I don't know whether I hope it's going to spot yet. Versus this direction.
No, absolutely not. It's not the ones who need are not the ones who
that's also true. Yes.
They can do enough without right?
Yeah, but I don't mean necessarily.
seconds?
Okay, good afternoon, everybody. This is last talk for today before the poster session, and it's a pleasure to introduce to you Tamás Kiss from the Wigner Research Center in Budapest. His title is Chaos Fractals and Phase Transition in the Dynamics of Qubits. Please.
Thank you very much. So I come from a faraway country, Hungary, and I'm very pleased that and grateful to Thomas and all the organizers to invite me here. This is my first time here in Mexico. And after this nice lunch, in this siesta time, I try to have something interesting, exotic, and hopefully exciting for you. This is a little topic I started to be interested in like 20 years ago. And since that, every now and then, I collaborate with people. So there is a quite long list from the Budapest group, students and collaborators. Also, we collaborate strongly with the Technical University in Prague. And we had a very successful collaboration in Darmstadt, and also one with, it's written here Beijing, but it was at that time in Nanjing in China, an experimental group you will see. So I was always interested in chaos, nonlinear systems, but then I turned my focus to quantum optics, and I thought that these systems are more like linear. And so it was a surprise for me that that there is something, there is a way to define and find nonlinearity in a very simple system, which is a little bit artificial. So it comes from quantum information originally, but which shows nonlinearity. So quantum mechanics is considered to be linear in general, especially a closed quantum system or quantum channels are in many cases treated as linear maps. However, there is a set of people who is interested in what would happen if quantum mechanics was or were nonlinear. And there is a small number of publications which treat this problem. For example, by Lloyd here, they showed, Abrams and Lloyd, that hard problems in computation theory, like MP-complete problems, would be easily solved in polynomial time if nature or quantum mechanics was truly nonlinear. Again, another problem like discrimination of non-orthogonal states, that would also be possible if we had some nonlinear systems in quantum mechanics. On the other hand, we have many-body systems which are described by some nonlinear equation, which we very well know. So, for example, a cold atomic gas, a Bose-Einstein condensate, has an approximate description by the Gross-Pitevsky equation, which is nonlinear. And so you can use this nonlinearity to design some of these protocols like quantum walks, and then you have nonlinear quantum walks. However, the underlying physics is still quantum mechanics, so this approximation should break down. And indeed, that is the case. And for example, in this paper, Meyer and Wong showed that a quantum search would be very efficient with these Bose-Einstein condensates. However, they stress that our results lead to quantum information theoretic bounds on the physical resources required for these effective nonlinear theories to hold asymptotically. Okay. But this is all not really the topic of today's talk, but a slightly twisted question. So we have the motivation from entanglement distillation, which is a typical quantum information protocol. You have many systems, entangled pairs, but somehow the entanglement was distorted by some noise. And so you do some operation, a set of operations by which you enhance the entanglement in a fewer number of systems. This is possible by local operations and classical communications. And we will come back to this question. That was the original motivation. Then we went to a much more simplified system in order to study it in much detail. I will show you. And after this detour, we came back to entanglement distillation again. So what happens in quantum mechanics, you can have measurements as well, projective measurements like von Neumann measurement, which are probabilistic. And then you gain some information from the system. And of course, you can use this information, which you gained, and feed back the information. For example, the simplest way is use post-selection. So according to your measurement result, you select some of your systems. And if you do all these together, you combine, then you might break linearity. How? Before going into this, this is just a preliminary introduction to a notation, which is very trivial. But in order to better understand what is going on, I suggest that you follow carefully this notation. So what do we have here? We have a single qubit, a two-dimensional quantum system, which is equivalent to a spin 1/2. And if you want to describe it, you need two complex numbers, A and B. But because you have a normalization and a global phase, in the end, you don't really need these two complex numbers. And effectively, you have two parameters. This can be also mathematically correctly seen by Hopf vibrations, but it doesn't really matter. For us, it's enough that instead of these two complex numbers, we can take their ratio, which is a new complex number, Z. So B divided by A is a Z. And in this way, we take care of the normalization, which is now a function of Z. And the global phase doesn't really matter. So we are left with one complex parameter, Z. And there are two nice ways to visualize this situation. So you can either use the block sphere, or you can use Z as it is as a complex number. So the complex number is on a plane, and the block sphere is, as the name shows, is a sphere. And effectively, you can view this block sphere as the Riemann sphere of the complex number Z. You have to be careful a little bit with the notations, but actually, if you start from the block sphere, you can use a stereographic projection, like using a map in cartography. It's a little bit strange map, but nevertheless, you can use it. And stereographically project each point of the block sphere to this plane. And this helps to visualize some of the features. Okay, so this was just a notation. But this notation was tricky and helped us immensely. So the very original starting point was a pioneering paper by Gizan, which caught our eye. And this is really an almost trivial thing. So you have two quantum states, two qubits, and both are in the same quantum state. This is natural in entanglement distillation, for example, where you think that you had the same noise affecting all the pairs of qubits which you have. But now we have only a single qubit system twice. So, or even an ensemble, and we take two members of this ensemble. They are in a pure state. And we apply a C-naught operation and measure one of the outputs in the natural computational basis. So it's very trivial. What happens? So the initial state with this Z notation was this, so 0 plus Z times 1. And since both of the qubits are in this state, we can write down the initial state as 0, 0 plus z times 0, 1 plus z times 1, 0 plus z squared times 1, 1. Now you apply the C0 operation. And what is the C0 operation? You exchange the last two of these basis states. So here, instead of 1, 0, you have 1, 1, and instead of 1, 1, you have 1, 0, because this is the conditional knot. Again, very trivial. And now we measure the target qubit, the second qubit, in the 0 state. So we have to choose the first member of this sum and the last one. And we have 0 plus z squared, 1. And this is very nice in our notation. In the original paper, it was shown that any density matrix has a similar property, namely, the density matrix elements are element-wise squared. So each element of the density operator, not as a matrix, but element-wise squared. But in this notation, it's even more trivial, maybe. We have z, and then we have z squared. So this is a function of z. This is the square function. Okay, and then the idea is that maybe also in entanglement distillation, if you can do one step, you have some better entangled state, but maybe you want even more entangled state, so you repeat again the step. But in order to repeat the step, you have to do the first step twice in order to have this input state for the second step twice. And if you want to do one more step, you have to do this whole procedure again from scratch. And so it can be seen that it will be needed an exponentially large ensemble as the iteration goes on with respect to the number of iterations. Nevertheless, this is doable. And so we can also turn this question and ask about the most general possible time evolution of a quantum system, including this type of procedures. And we will show that this will contain some features which are usually not there in the time evolutions people consider. So if we go back once, just to see, so this is a deterministic operation. You just square this, but from a given input state, you are for sure that you get this output state. There is a probability involved in measuring the 0 state, but once you take into account the post-selection, then the resulting state is deterministic. So it's deterministic. Pure states become pure states. And this suggests already that maybe complex deterministic chaos may emerge. And this is indeed the case. I will show you some details about it. And then you can ask many, many questions. Pure or mixed initial states, closed or open evolution, and you might even go higher dimensional Hilbert spaces. We will mostly focus on two-dimensional, but in the second half of the talk, I will mention some results about qubit pairs, so four-dimensional systems. So let's go back to square. So z square, what happens if you square a complex number? And you square it again. And you iterate this procedure. Oh, this is very simple. If the absolute value was smaller than 1, you get smaller and smaller and smaller values. So all the numbers within this unit disks, this means a set of possible initial states, of course, all these converge to 0. And outside of the unit circle, they converge to infinity. And the 0 and the infinity are just the two computational basis states. But already in this very simple example, there is one strange region, a circle, the unit circle. If you are starting from the unit circle, then the absolute value doesn't change. However, the phase changes and it doubles. And if you double and double and double the phase, it goes around like crazy. And it is indeed crazy or chaotic. So you can calculate the Lyapunov exponent on the circle, which is positive. Okay, let's go back to the block sphere picture. So this means that all states on the upper hemisphere of the block sphere tend to the one of the poles, which is the 0, and all the ones in the southern hemisphere will eventually converge to the 1 basis state, which is the other pole, the north pole. And the Julia set is the equator. So the Julia set is defined in this very good book by John Milner, Dynamics in One Complex Variable, from which we learned many, many things about these mathematical features of iterated complex functions. I will come back to this later. And so let's now change a little bit the topic and go back like 7 years and to a collaboration which we had with a Darmstadt group led by Gernot Albert, and somebody from the audience, Mauricio Torres, was also collaborating on this. So we were searching for a physical system realizing such maps. And it is a quite complicated system, which I will not show you in any detail because I don't have time. But this is a kind of Davis-Cummings scheme. So 2 atoms are crossing a cavity, and then you measure also the cavity field. And if everything goes and you have a few approximations, then the outgoing 2 atoms suffer an entangling operation. And this entangling operation is a little bit similar like the C naught, but it is not the C naught, something else. And we analyzed this a little bit. So this is the unitary operator, okay, whatever it is. And then you can construct the corresponding function, which is not a square function anymore, but something like this. And then what you find that on the complex plane, it is now the imaginary axis which divides the 2 convergence regions. Okay, back to the block sphere picture. Oh, the block sphere picture simplifies our way of thinking because on this block sphere picture, it's just a rotation. Nothing else happened, just we rotated the ball. And it appears instead of a circle as a line, the Julia set, it's only because of this stereographic projection, which is strange. And it's clear that we discuss asymptotic features sometimes. So after many, many iterations, which is not very feasible. But here we showed that even after a few number of iterations, I think the number of steps was 3 here. It's really not a really asymptotic number, no, 3. Even after 3 steps, 2 states, this is just some numerical examples. So there were 2 states overlapping like 0.92. I think an absolute square should be here. And then after 3 steps, their overlap is only 0.08. So it's quite good. They orthogonize quite quickly. So this type of protocol might be used for orthogonalization. And actually, you can distort this. So instead of the equator or a rotated equator, you can design any small circle on the sphere and require that inside this circle you converge to 1 reference state, and outside of the circle you converge to some orthogonal state. And you might think about it that I have some small error. I would like to have this reference state. I have some small error, and I allow this epsilon radius circle as my allowed error. So everything inside this should then converge to my reference state. Everything outside this to the orthogonal state. So it might have some useful application. This is some numerical example again. Okay. Now these were specific examples. What is the most general thing you can achieve? And the answer is was given by András Guillen in collaboration a few years ago. Namely that there is a almost like one-to-one correspondence. It's not one-to-one, the correspondence, but there is a nice correspondence between unitaries and certain complex functions. And these complex functions have this form. So these are rational functions of second-order polynomials. This is the most generic thing which you can get for a qubit if you allow for arbitrary unitaries. And it's constructive in both ways. So from the unitary, you can construct such a function. And from such a function, you can construct a unitary. It's not unique, the construction, but it's constructive. And also, we derive the quantum magnification bound, which means that if you have some operations which allow for distinguishing states somehow after a number of steps, then this necessarily requires exponentially many initial states as a function of the iterational steps. Okay. So now maybe some historical remarks. So this, what we encountered, these rational polynomials, belong to one branch of mathematics, which started a little bit more than 100 years ago. By the very first publication I could find was maybe this one by Ernst Schröder, Über iterierte Funktionen. But there he did not explain too much about complex functions, just iterative functions. But a few years later, there was an interesting kind of competition amongst French mathematicians. Pierre Fatou, Gaston Julia, Samuel Latte. This is Schröder, the first one. And then Pierre Fatou and Gaston Julia. He participated in the First World War and lost his nose, unfortunately. And then Samuel Latte. And then after a few years, in the meantime, there was not so much interest in these functions. But after a few years, computers came, and Benoit Mandelbrot could use computers to visualize and study more and more properties of the fractals. And this is the part of the story which probably you already know. And so the first weird function was this one, z square over z square plus 2. And without any numerics and computers and visualizations, they could derive a number of properties of these iterated functions, their convergence, these fractal sets which they form, and so on. And I again stress that this book is very good by Milnor, so it's worth studying. Okay, now let's come back to the C-node gate. So we have the C-node gate. But in order to complicate a little bit the problem, we have the C-node gate and then a single qubit rotation after the C-node gate. So it sounds innocent, no? So the C-node entangling the two qubits, and for the remaining qubit, a one qubit rotation. And the one qubit rotation, for our purposes, is enough to describe it with these two parameters, a theta and a phi. And we combine this theta and the phi in this way, a tangent and e to the I phi, to have a complex parameter. And using this complex parameter, our function will look like z squared plus p over 1 minus p star, which is complex conjugation, times z squared. So is it very different or not from the circle and the two convergence regions? Well, the answer is it's very different. So that's what you get as a function of the parameter. So it's this very, very innocent quantum. It's like a minimal quantum computer, actually. So one C-node gate and one parameterized single qubit gate. And you take this primitive quantum computer, you also do measurement, as you should in a quantum computer, and then you repeat this procedure in an iterative manner. And what you get is chaos, really chaos, characterized not only by Lyapunov exponent on the circle, but even the convergence regions are bounded by fractals. So this is a slightly distorted circle, but it's already a fractal. But if you change the parameter more, you encounter stranger and stranger fractals. And some of them look like connected, some of them are disconnected. And there are these nice theorems from the Milnor book. So you can know in which case you are connected, in which case you are disconnected, for example. And there is this picture, which is a little bit interesting because there is a lot of blue in it. So let me remind you. So the blue means those points which do not converge. So the white points, these are initial states on the Bloch sphere. The white points converge somewhere, but the blue points do not converge. And here there are like visually very many blue points. On this picture, it's still a zero measure set, but then the question arises whether you can have a non-zero measure set of chaotic initial states. And this goes back to the work of Samuel Latte, because he worked out that, yes, mathematically speaking, such maps exist. They are called now Latte maps. And for those, all initial states are chaotic. And actually, there is a very nice duality, which is a mathematical theorem. So this Julia set of chaotic initial states is either zero measure set, or it is the full set of initial states. So there is no other set, no Fatou set. The complementary set is called Fatou set. This is also a duality theorem. Each point can be decided whether it belongs to the Fatou set, which converge somewhere, or the Julia set, which are the unstable fixed cycles and the chaotic points. There's a more precise mathematical definition, but for us it's enough. Okay, so there is a nice mathematical trick with which you can prove this theorem. And if we want to visualize these chaotic, all initial states chaotic, then we might choose something very simple, namely whether the absolute value of our z parameter is larger than 1. So this means that one of the basis states are more dominant. These are the black points, or the other basis states is more dominant, that are the white points. And so this is the without any iteration. This is just a unit circle. But if you iterate the map, then you get increasingly complex, more and more complex structures, a little bit reminiscent of a chessboard. And these small black and white patterns are finer and finer. And this means that you have an initial state and you move a little bit. And then after a number of steps, instead of one basis state being the dominant, the other becomes dominant. So it shows some kind of sensitivity to the initial condition. If we come back again, so we constructed this matrix, okay. So you can realize this in some physical system. And what you can really show that every initial state is chaotic and the system is ergodic in the following sense. If you choose one initial state and a very small neighborhood around this initial state, and then you take all possible initial states from the neighborhood of the reference state, then after a finite number of iterations, you cover the whole Bloch sphere without exception. So there is only a finite number of iterations and you cover everything. So in this sense, it's ergodic. Okay, ergodic. But these are all pure quantum states. So what happens if we introduce some experimental noise? And first, we focus on the initial state noise, which means that instead of a pure state, we have some mixed initial state noisy. Does noise destroy this property? Well, in order to answer this question, we have to go to the density matrices and their evolution. And their evolution is slightly more complicated than the pure states. Nevertheless, we can describe the Bloch sphere coordinates because on the Bloch sphere, the outer points on the surface are the pure states, and the inside points are all the mixed states. So you can use a nice coordinate system, U, V, W, to describe all the points, all the possible mixed initial states. These are the usual Bloch sphere coordinates to parameterize a one-qubit density matrix. And then you can derive the iterative rule. The slight problem is that there's no book by Milnor, so we cannot really prove things so easily. Nevertheless, we turn to numerics, and we can see that asymptotically, all mixed initial states converge to the completely mixed state. So the first answer is that noise destroys this property. Everything will be the completely mixed state. However, we can ask whether this system can be realized experimentally. And for this, you would need that there is some small noise only. And whether with a small noise and a finite number of iterations, you can cover, well, not really the surface of the Bloch sphere, but somehow the Bloch sphere a little bit under the surface or something like this. And we could answer this only numerically, but the answer is yes. This is a picture which I only show because it's, again, a numerical example. So you take only 9 iterative steps, and there is, in these spherical coordinates, there is only a 10 to the minus 3 uncertainty at the beginning. And after 9 iterative steps, you cover all the possible directions. So there is hope that one can show something like this experimentally. And we indeed collaborated with an optical group. And well, we couldn't go to 9 steps. In one, so we could go for 2 steps, basically. I will not go too much into the details. So it's an optical experiment with down-converted photons. It is quite standard, these elements. So you can realize a CNOT operation and a 1-qubit operation as well. And you have conditional measurement on the initially entangled photons. And thereby, you realize the qubits. And we could do, here we could do 1 step of the protocol, and then we repeated this 1 step again. But, well, the results are just showing that in this particular experiment, the noise was not very big. So at least for these 1 and 2 steps, they coincide more or less with the expected values of the parameters. Okay, and this is another interesting possibility, which we heard about in another talk by Adrian Ortega a few days ago. Namely, you can experiment now with quantum computers as well. And why not realize such a protocol in quantum computers? And this is an early example. A few years ago, my former student, András Guillen, he realized such protocols, especially the latte map in a quantum computer. But of course, these quantum computers are very noisy, so he could realize only 1 and 2 steps. And well, it was, this is, the left is the theoretical value, the right is the quantum computer picture. And this is the initial state, that's okay. After 1 step, you see something. After 2 steps, you don't really see anything. But that was back then in 2019. They put it on the archive on 21. I think it's not published anywhere, but it's on the archive. So quantum computers developed since. Okay. How much time do I have? 5 minutes. Oh. Okay, so I will be very quick, but so there is a workhorse for us when a special case when you have the Hadamard operation here, and there the initial fractal is the spider web-like fractal. The question is whether it is destroyed by noise. And go over to on these calculations, because I don't have time. But what we find that if we change the purity of the initial state, then the fractal dimension remains the same. So up to a critical value, and this critical value is very interesting. There the fractal disappears completely, and you have only blobs without the fractal nature of their border. So what is this critical purity? This can be a little bit better understood if you analyze the inside of the Bloch sphere. I don't go through the full analysis here. I just only mentioned that there is one particular point which you can find analytically, this C1, which is an unstable fixed point within the Bloch sphere. And this kind of phase transition is related to that unstable fixed point that can be cross-checked by backwards iteration as well. And if you are interested in this topic, there will be a poster by Attila Portik on these and also higher order protocols with a similar nature. I jump over these results, and I just come back to the qubit pairs, where entanglement distillation was a question. So what we do here is we have qubit pairs in the same initial state. A is one qubit pair and B is another qubit pair. And one member of the qubit is at one laboratory, and the other member of the pair for each pair is in another laboratory. So they can do some local operations here, and they can classically communicate the measurement results. And so I can still write down the initial state formally, but the problem is that we cannot use this trick of introducing a single complex number or even two complex numbers. It's not enough. This Hopf vibration shows us that you need 7 real variables, which is too much. So this trick doesn't work. And we struggled with this, and we came up with a very nice solution with a student from Prague. And this trick is that, first of all, you take only special initial states, like 0, 0 plus 1, 1. It is like a Bell state, a very good entangled state. And you distort it in a certain way. You allow a parameter R, which is a complex number. And the second trick is that you apply 2 iterative steps instead of 1. And after 2 iterative steps, you can figure out that your state is again the same form as the initial state. So this is like a subspace. Of course, it is a nonlinear dynamics, so I shouldn't say subspace, but this is an invariant set of states which remain the same after each second step of the dynamics. And what happens? The initial states can be described by the same function as previously, but the meaning is very different. So these represent each point an initial qubit pair. And the green means that asymptotically they are fully entangled, and blue means that they are separable. Actually, the blue states tend to a cycle, but both members of the cycle are separable. So this means that if you change the initial state a little bit, like here, where they are very dense, you change the initial state a little bit, and instead of a completely entangled state, you end up with a separable state. So this is a little bit important for entanglement distillation. We applied similar ideas to 3 qubits, which I cannot go into the detail. I jump over it. And I come to my conclusion. So I talked about the realization of these nonlinear protocols on quantum computers, and this is an ongoing research, as you could hear from Adrian's talk. Then there is another interesting thing, is that understanding better these nonlinear transformations, we could design a new distillation protocol, which is under on the archive now, and we should publish it soon, I hope, at least. And this has the property of arbitrary initial, not too noisy arbitrary initial states are distilled to a certain bell pair. So it seems like a quite efficient way of producing a very well-defined, maximally entangled bell pair. And as a bonus, the noise will be diminished quadratically, meaning that if you had an epsilon noise, so any noise term, which is proportional to a small number epsilon, then after all these operations, you have a noise term which is proportional to the square of this epsilon, which should be much smaller. And as you could see in this last part of the talk, which I jumped over, you can generalize it to 3 qubits and even more qubits, so like a network of qubits, and we are working on this right now. So thank you for your attention.
Thank you very much. Other questions?
So can you use this as models for decoherence and dissipation somehow? Because it's very, very simple and
I was always thinking in terms of as a measuring device of coherence and dissipation, and that's why we try to apply this in quantum computers to test whether how much noise is there and whether it distorts or not. This protocol I don't really know because it takes pure states to pure states and it's deterministic in the first part. So I think in terms of more like this deterministic chaos dynamics, but one can contemplate whether you can somehow connect it to other noise models. Yes.
More questions? Okay, I have a question. If you do error correction, say bit flip, for instance, you can also see it as a nonlinear map. It's just of the same type. And you would say that it improves the purity of the state. So what about combining, say if you have a non-perfect initial state, you could combine these chaos-producing maps and error-correcting maps to get something?
Yes, thank you for this remark. I wanted to mention it, but I forgot. Yes, there is indeed a relation to error correction. And sometimes also entanglement distillation is called purification, which I don't really like because purification has also other meanings. But it's a definite property of these protocols that the purity of the state can increase. And also this convergence to the reference state shows that it's a little bit like similar to error correction. Yes, the answer is yes, you can combine it with error correction models, and we have thoughts about it, so yes.
Okay, if there are no more questions, then thank you again. Before you leave, one quick announcement. So if you need a certificate for participation, and then please tell us or write